Hello there, everybody. It looks like I am live. So this is in this video, this live video that I'm doing, I'm going to be responding to a video that William Lane Craig did at the Physics Philosophy, the PhysPhil conference of 2012. I have watched this video before. It's definitely been a number of years. I was watching some of it about 4 days ago. I got maybe 10 minutes into it. And I just like I need to do a response to this. So I don't remember everything that's in the video, so I might be surprised by some things that I hear, even though I have seen this. But let's just jump right into this. It is about an hour and 10 minutes long, so I'm assuming this stream will probably go for a couple hours. I guess it depends on how much there is that I need to respond to. But this is a video on Einstein's special theory of relativity, time, and God, and including God's relation to time. And for anybody that knows William Lane Craig and his particular interpretations of physics, he rejects Einstein's special theory of relativity. He opts for a Lorentzian aether theory, which no reputed physicist is going to hold to for a number of reasons that we will cover in this video. I have fast forwarded the video a little bit because there was a bit of an introductory period there that we don't really need to listen to. So let me just double check and make sure everything is sharing correctly. Yes, it is. Beautiful. Beautiful. And let's get started. Also, I did want to mention quickly that the audio in the video, it has nothing to do with StreamYard or anything. It's the video. It's not very, I need to turn mine down a little bit. It's not very high quality, so I'm really hoping that everybody will be able to understand what it is that he's saying. If not, I will link I will put a link to this video in the description just because, but I'm really hoping that the audio can be followed along with. Just as a quick disclaimer, I probably am going to let this beginning part where he's kind of introducing his ideas and what have you go for a couple minutes. There's really not much of substance that at least I think is worth responding to here. So it's not just like we're going to sit here in silence and watch this, but this beginning part here, I probably will let go for a minute or two. I just wanted to point out, notice how we're already having to explain away a bunch of notions with the idea of God having a relation to time. I'd also be curious what I guess I don't know how to interpret something existing but being timeless, like not having a sense of temporality, because then I would assume, following from that, it likely doesn't have any spatiality. It's not in space either, given that at least classically space and time are connected into a unified manifold. Whether that holds true entirely at the quantum level of reality, we don't yet know. But classically, that is the case. So I would take it that God wouldn't exist in space either. And at that point, I'm just curious what it is that we're even talking about. So, really quickly, what he did is he explained the difference between the concept of time. It's sort of a Newtonian concept. Time is this absolute, immutable backdrop against which everything is measured. Special relativity says, no, it's not. It's a physical, fundamental aspect of reality, and it can be affected by things inside of it and can affect things inside of it, which what William Lane Craig says there is an interesting question. If God is in time, whose time is he in? I I guess if I were in his shoes, I would just say God exists at all times. He's just purely extended through the dimension of time, regardless of how one maps coordinates in it. But I don't know if such a response would be appealing to Dr. Craig or not. Let's continue. Yeah, so what he's essentially saying is that yeah, there's no absolute frame of reference, and so for time, and so if you were going to ask what time is God in, well, well, he's just in his own time. He is the privileged reference frame. It's that seems a little, what would that be, post hoc? That seems, yeah, that just that's a little funny. The thing is, a lot of these issues he's raising, I don't actually think would be valid problems for a theist who took to a tenseless view of time. Because, I mean, if the tenseless theory of time is true, then what he's saying about our own consciousness would have to be true, and I don't think that it is. So it seems that actually under a tenseless theory of time, you could probably more easily argue for how you could more easily present the argument that he seems to be giving for how God is related to time. Okay. So I just got a message. You guys can hear me. Sorry I wasn't able to watch the chat because in order to keep it full screen, I have to be in YouTube. But I just got a message from Twitter that you guys can't hear and haven't been hearing. I'm going to be honest. Most of what he has said thus far really is not that interesting. I mean, if you guys want me to replay it, I can. If you guys just want me to keep going from where it was at, just let me know in the chat. I personally don't think what he was... What? This is interesting. Oh, I know what I did. I know exactly what I did. I was sharing YouTube through the app rather than through a Chrome tab, and when I share it through the app, audio doesn't come through. Yeah, that's right, because I guess that's just the way they want to build their app. I wouldn't have done it that way. Anyway, let me get this pulled up in Chrome here and then share it. And when I do so, Chrome tab. There we go. Share tab audio. Alrighty. Now we should be good to go. I'm just gonna sit for a minute or two while people, I don't know how many are in the chat. It doesn't show me here in StreamYard, but let me know whether you guys want me to start, go back about 5 minutes and go through it all again, or whether you just want me to pick up from where we're at. All he's really been doing is giving an explanation of how God's relation to time can be negatively affected by the ideas presented by special relativity. So it really hasn't, we really still haven't gotten into the meat of what he presents in this video as far as I can remember. So Vesta says the less William and Craig, the better. So I'll just take that as we'll just start from here. So hopefully everybody can hear it now.
If God is temporal, he exists in either the time associated with a single inertial frame or the times associated with a plurality of inertial frames. 3, therefore, if God is temporal, he exists in either the time associated with a single inertial frame or the times associated with a plurality of inertial frames. 4, God does not exist in either the time associated with a single inertial frame or the times associated with a plurality of inertial frames. 5, therefore, God is not temporal. How shall we assess this argument? Well, let's look at premise 2 first. Premise.
I know I said that the audio might be a little iffy before I actually started the video, and I'm sure you guys are now capable of telling that this was recorded in 2012 on probably a camera from like 2006. But when I said that there might be some, the audio might be a little difficult to hear, I wasn't expecting it to be completely silent. Oh, Lord.
2 is at best misleading in that it fails to take into account the fact that STR is a restricted theory of relativity and therefore is correct only within prescribed limits. It is a theory which deals with uniform motion only. The analysis of non-uniform motion, such as acceleration and rotation, is provided by the general theory of relativity, hereafter STR. STR cannot therefore be expected to give us the final word about the nature of time and space. Indeed, within the context of GTR, a new and important conception of time emerges. For GTR serves to introduce into relativity theory a cosmic perspective, enabling us to draft cosmological models of the universe governed by the gravitational field equations of GTR. Within the context of such cosmological models, the issue of time resurfaces dramatically. All contemporary cosmological models derive from Russian mathematician Alexander Friedmann's 1922 model of an expanding material universe characterized by ideal homogeneity and isotropy. Although GTR does not itself mandate any formula for how to slice space-time into a temporally ordered foliation, nevertheless, certain models of space-time, like the Friedmann model, have a dynamical, evolving spatial geometry whose natural symmetries guide the construction of a cosmic time. In order to ensure a smooth development of this geometry, it will be necessary to construct a time parameter based on a preferred slicing of space-time. Now, as a parameter independent of spatial coordinates, cosmic time measures the duration of the universe as a whole in an observer-independent way. That is to say, the lapse of
That's so I knew that this was the point that he was getting at. I was just waiting for him to get through most of it. He's referring to something in cosmology known as cosmic time. It's not what he means when he says observer independent is not the kind of observer independent that cosmic time is. It is entirely arbitrary. What cosmic time is the amount of time elapsed on the clock of the universe, so to speak. It's literally just a synonym for the age of the universe. It's arbitrary because it is a clock. We take it as a clock that does not feel the expansion of space-time, nor is it affected by any matter distribution overs or unders, more matter, less matter, that would result in time dilation. It's essentially a clock that we take ideally as having zero time dilation effects on it, and that was sitting at t equals 0 at the instant that we arbitrarily define right now as well, t equals 0 as the Big Bang. The earliest we can go back with our physical models, we just set the clock to equal to 0, then we ignore any time dilation effects on it, and we let it tick at 1 second per second, and we get about 13.8 billion years. This is arbitrary. This is 100% a convention that we utilize to aid us in the descriptions of the universe that we have through models like GTR. But when he says it's observer independent, not in the sense that he's wanting people to think that it is an actual physical preferred temporal frame of reference, because that isn't what it is. This is much like if you could take something like the ideal gas law and apply it to time for cosmology, where you just ignore all the dilation effects that would occur on this clock and measure out as a result of that what elapsed time that clock would read. So no, I don't. That should be scheduled for tomorrow. That's tomorrow. I wouldn't have been able to schedule anything today. I wasn't pushing this back any further. So getting back to the stream, that's what he's explaining, the concept of cosmic time. And it is not a universally preferred frame of reference. It is an arbitrarily preferred frame of reference that does not actually have any physicality in reality. It is not an actual preferred frame of reference objectively independent of any observers. It is arbitrarily decided by observers. Us.
Cosmic time is the same for all observers. Nevertheless, cosmic time is related to the local times of a special group of observers called fundamental observers. These are hypothetical observers who are at rest with respect to the expansion of space itself. Cosmic time relates to these observers in that their local times all coincide with cosmic time in their vicinity. Because of their mutual recession, the class of fundamental observers do not serve to define a global inertial frame, technically speaking, even though all of them are at rest. But since each fundamental observer is at rest with respect to space, the events which he calculates to be simultaneous will coincide locally with the events which are simultaneous in cosmic time. What this implies is that, contrary to premise 2, it does not follow from the correctness of STR that if God is in time, then he is in the time of one or more inertial frames. For if God exists in cosmic time, there is no universal inertial frame with which he can be associated.
So God exists in a time arbitrarily defined by humans under an assumed ideal set of conditions to aid us in modeling physical reality. That seems like an admission that God doesn't really exist because, again, cosmic time is not an actual physical time. It is an arbitrary time that we decided upon and utilized. So it seems that he's misunderstanding what precisely cosmic time is meant to be. It's not actually a physical time. So there is the frame of reference associated with it is 100% arbitrary. It doesn't really map to anything that's physically in reality.
But let that pass. Although it may come as something of a shock to many, it seems to me that the most dubious premise in the foregoing argument is premise 1. In order to understand why I say this, it will be helpful to take a backward glance at Isaac Newton's classical doctrine of absolute time and space, which was superseded by STR. The locus classicus of Newton's exposition of his concepts of time and space is the scholium to his definitions in the Principia Mathematica. In order to overcome what he called common prejudices concerning such quantities as time, space, place, and motion, Newton draws a dichotomy with respect to these quantities between absolute and relative, true and apparent, mathematical and common. With respect to time, he asserts, and I quote, absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external, and by another name is called duration. Relative, apparent, and common time is some sensible and external, whether accurate or unequal, measure of duration by the means of motion, which is commonly used instead of the true time, such as an hour, a day, a month, a year. The most evident feature of this distinction is the...
I have a feeling that what William Lane Craig is about to argue is that, relativistic effects on time, like time dilation, are just features of how we choose to mathematically represent time. They're not actually representations of physical changes in physical time. I have a feeling that he's going to make that argument. Let's see. I could be wrong.
Independence of absolute time from the relative measures thereof. Absolute time, or simple duration, exists regardless of the sensible and external measurements which we try, more or less successfully, to make of it. Excuse me. Newtonian time is thus, first of all, absolute in the sense that time itself is distinct from our measures of time. But Newton also conceived of time as absolute in yet a more profound sense. Namely, he held that time exists independently of any physical objects whatsoever. Usually, this is interpreted to mean that time would exist even if nothing else existed. that we can conceive of a logically possible world which is completely empty except for the container of absolute space and the flow of absolute time. But here we must be very careful. Modern secular scholars tend frequently to forget how ardent a theist Newton was and how central this theism played in his metaphysical outlook. In fact, Newton...
I feel pretty confident that these secular scientists Dr. Craig speaks of are well aware of this fact. It isn't something that's like, this isn't knowledge that I would say is uncommon about Newton. And yet Newton's concepts of time, although admirable and maybe appealable, are generally regarded as incorrect.
Makes quite clear in the general scholium to the Principia, which he added in 1713, that absolute time and space are constituted by the divine attributes of eternity and omnipresence. He writes, God is eternal and infinite. That is, his duration reaches from eternity to eternity. His presence from infinity to infinity. He is not eternity and infinity, but eternal and infinite. He is not duration or space, but he endures and is present. He endures forever and is everywhere present. And by existing always and everywhere, he constitutes duration and space. Since every particle of space is always, and every indivisible moment of duration is everywhere, certainly the maker and Lord of all things cannot be never and nowhere. Because God exists, there exists an everlasting duration. And because he is on...
Yeah, Isaac Newton kind of had this idea that God was space-time in a sense, or at least maybe more, you could say more was like a ground for space-time. But that would just come down to how one's choosing to interpret Newton. If you took what he's saying in a more literal context, you might interpret it as him saying that, what the fuck is in my eye? That God essentially is space-time. God grounds duration and grounds extents in the spatial sense of that term, and thus God would be space-time. Or you could say that space-time is something separate from God, but grounded in his being, so that if God is, space-time is, and that there is a duration through it. Again, this would be Newton's view. I don't know that William Lane Craig is necessarily espousing that. I think he's just reading from it to help make his point.
Omnipresent, there exists an infinite space. Absolute time and space are therefore relational in that they are contingent upon the existence of God. In Newton's view, God's now is thus the present moment of absolute time. Since God is not, quote unquote, a dwarf God located at a particular place in space, but is omnipresent, there is a worldwide moment which is absolutely present. Newton's temporal theism thus provides the foundation for absolute simultaneity. The absolute present and absolute simultaneity are features first and foremost of God's time, absolute time, and derivatively of measured or relative time. Thus, the classical Newtonian concept of time is firmly rooted in a theistic worldview. What Newton did not realize, nor could he have suspected, is that physical time is not only relative, but also relativistic, that the approximation of physical time to absolute time depends not merely upon the regularity of one's clock, but also upon its motion. Unless a clock were at absolute rest, it would not accurately register the passage of absolute time. Moving clocks.
You say a clock at rest, Dr. Craig, at rest with respect to what? this is the thing with relativity. The very concept of being at rest is itself with respect to something else. We would all think, assuming that we're sitting in chairs or what have you, that we are at rest, but we are only at rest with respect to the earth. I mean, obviously the other objects around us, like your desk and my laptop and things like that, but we are at rest. We define us being at rest with respect to the earth. The earth is rotating and orbiting the sun. The sun and thereby the entire solar system are moving around the Milky Way galaxy, which is itself rotating and is moving through intergalactic space toward the Andromeda galaxy, and all the galaxies and all of the superclusters of galaxies are slowly moving and writhing through space-time. So when you say a clock at rest with respect to what? This is the notion of relativity. Motion is only relative. If you were moving and there was literally nothing else around you to measure, you would have no idea to tell that you were moving. You would not be able to tell that you were moving, even if you did contain some sort of intrinsic motion. But this is sort of the thing, is that does anything in reality contain intrinsic motion, motion that exists independently of it being measured relative to anything else? And at least as I understand it, that is a bit of an open question in physics as well as philosophy of physics, but I think it is an interesting one to ask.
Run slowly. This truth, unknown to Newton, was finally grasped by physicists only with the advent of relativity theory. Where Newton fell short then was not in his analysis of absolute or metaphysical time. He had theological grounds for positing such a time, but in his incomplete understanding of relative or physical time. He assumed too readily that an ideal clock would give an accurate measure of time independently of its motion. If confronted with relativistic evidence, Newton would no doubt have welcomed this correction and seen therein no threat at all to his doctrine of absolute time. In short, relativity corrects Newton's concept of physical time, not his concept of absolute time. What Einstein did, in effect, was simply to remove God from the picture and to substitute in his place a finite observer.
Wait, but hold on. When we say remove God from the picture, when was God ever like actually in the picture? But we can't just assume that because Isaac Newton, who laid the groundwork for modern physics, the foundation for modern physics, believed in this concept of absolute space and time, either as God or grounded in God, does not mean that that's actually what like the science said. God was never like legitimately in the picture. So that statement's quite curious, but I mean, Dr. Craig is a theist, so naturally the way that he looks at the world is going to be drastically different than someone like me who's a naturalist.
According to historian of science Gerald Holton, thus the relativity theory merely shifted the focus of space-time from the sensorium of Newton's God to the sensorium of Einstein's abstract Gedanken experimenta, as it were, the final secularization of physics. By rejecting Newton's absolute time and space, and along with them, the ether, relativity theory left behind only their empirical measures. Since these are relativized to inertial frames, one ends up with the relativity of simultaneity and of length. What justification did Einstein have for so radical a move? How did he know that absolute time and space do not exist?
Because the very concept of absolute doesn't make any sense. The principle of relativity, this idea that motion is only relative to something else, has actually been around for several hundred years, since even before Isaac Newton. So the idea of relativity is not actually, it did not come with Einstein. Also, when we look at reality, the fact that we measure differences in space and time relative to motion seems to itself imply that these aren't absolute things. These are things that only have some sort of meaning depending on how you choose to measure them with respect to other objects. And this is seen explicitly in electromagnetism. In fact, it was people like Heinrich Lorentz, Henri Poincaré, and then eventually Albert Einstein who pulled special relativity out of classical electromagnetism. Humans would have developed special relativity regardless of who did it, because we had electromagnetism. That's where this whole concept of the ether came from in a lot of the earliest attempts at what is ultimately now the special theory of relativity.
The answer, in a word, is verificationism. Historians of science have demonstrated convincingly that at the philosophical roots of Einstein's theory lies a verificationist epistemology mediated to the young Einstein through the influence of Ernst Mach, which comes to expression in Einstein's analysis of the concepts of time and space. In 1905, when Einstein published his paper on the electrodynamics of moving bodies, and for several years thereafter, he was a self-confessed epistemological pupil of Mach, and the epistemological analysis.
Did this guy really say that the philosophical concept of verificationism is contained in special relativity? No. I don't know if Einstein was himself a verificationist. I don't really know all that much about his personal philosophies and things, so I'm just going to refrain from commenting on that. But regardless of whether Einstein was himself personally a verificationist, and I do know it is true, Einstein picked up a lot of his philosophical thought processes from people like Ernst Mach and David Hume. But again, regardless of whether Einstein himself believed in a verificationist epistemology, I don't really think has any bearing on the particular theory that he developed. Many of the aspects of it came even before Einstein, like the concepts of length contraction and time dilation, which were a result of the Lorentz transformations that were originally added into electromagnetism to help preserve some of the symmetries that we observed in electromagnetism. Einstein simply utilized those to redefine what are called space-time intervals are in special relativity. So not all, but a lot of the concepts of special relativity were around prior to it, developed and understood and believed by men whom likely probably weren't verificationists themselves.
Of space and time, given in the opening sections of this paper, clearly displays this influence. Mach's positivism manifests itself most clearly in Einstein's a priori rejection of absolute time and space and reliance on operational definitions of.
I'm going to need to hear an argument for how Einstein's rejection of absolute space and time was a priori. That seems to be saying that he rejected this notion of absolute space and time and then used that to formulate this thing called special relativity, rather than that he was formulating this thing called special relativity, which he did over several years, in his own words, 7 and more years, and eventually came to abandon the notion of absolute space and time. Because, and I've been doing quite a bit of reading, just especially on the more so the history of specifically the development of special relativity, rather than just understanding what it is. And it seems that is exactly what it was with Einstein. Well, number one, the notion of absolute space and time are already called into question by most physicists because of the principle of relativity and because of electromagnetism. And then Einstein, when trying to develop what special relativity was and really think about these problems, he didn't know at the time that he was developing special relativity, but when he was thinking about these issues and trying to find explanations for them and trying to explain away the problems, that's what led him to developing special relativity. And looking at the world that way and realizing that this is the way the world works led him to abandon the notion of absolute space and time. I don't know if he even held those notions to begin with, but I don't think those had much of a bearing on his development of special relativity. I think that was him examining the empirical data that he had available to him at the time, and utilizing that to try to better explain the things that we observed in our reality.
Crucial concepts. Absolute time, or a privileged frame, is presumed not to exist because, quote, To the concept of absolute rest, there correspond no properties of the phenomenon, end quote. It is taken for granted that, quote, all our judgments in which time plays a role must have a physical meaning. When it comes to
this stuff, it feels like Dr. Craig is arguing that this stuff was just kind of assumed without any real reason and a theory developed on it. None of this is true. There were good observational reasons for denying the notion of absolute space and time, primarily because, number one, reality doesn't behave as if there is an absolute space and time. Number two, reality doesn't behave as if it's space and time are separated things. And number three, there isn't a meaningful way to describe space-time in any absolute sense to begin with. Nobody's ever been able to do it. Dr. Craig does it by just saying, well, it's God's spatio-temporal frame of reference that is absolute, which to me seems, I don't know if I would say, well, I suppose you could argue that he's a priori assuming God and then working from there, but that's getting into the weeds a little bit, and I don't want to assume anything about Dr. Craig that may not be true because I like to be charitable. But yeah, I don't think that these things are really assumed a priori to the development of this. I think that they were assumed because it's exactly what the mathematics and what the physical experiments that were being done on trying to measure an ether and how it affects light and how motion through it of things that are emitting light and how it changes. And all of those experiments were exactly the opposite of what we would expect it if there were an ether, which is really where Einstein started to think, because it was there were effects that took place. And he said one of two things has to be wrong. Either there isn't an ether, and most people at the time believed there was one because electromagnetism is a wave, electromagnetic radiation is a wave, and all waves that we'd ever seen before propagate through some medium, so there has to be some medium that they're propagating through. But his observations also led him to assume that, well, if the ether is true, then the principle of relativity has to be wrong. And the principle of relativity, based on our observations, does not seem to be wrong. And that's when he started to assume, yeah, that maybe there isn't this thing that we call an ether. And that led into further thought experiments, and that eventually led to him developing special relativity.
Concerning the simultaneity of distant events, the concern is to find a practical arrangement to compare clock times. In order to define a common time for spatially separated clocks, we assume that the time light takes to travel from A to B is equal to the time it takes to travel from B to a definition which presupposes that absolute space does not exist.
Not really. It's more that this is like leading into, I believe, the constancy of the speed of light things. That doesn't presume or presuppose. I suppose, yeah, you could call it a presupposition, but that doesn't make it unjustified. Presuppositions are not necessarily unjustified things.
Thus, time is reduced to physical time, clock readings, and space to physical space, readings of measuring rods. And both of these are relativized to local frames. Simultaneity is defined in terms of clock synchronization via light signals. All of this is done by mere stipulation. Through Einstein's operational definitions of time and space, Mach's positivism triumphs in the special theory of relativity. Reality is reduced to what our measurements read. Newton's metaphysical time.
Well, I mean, that's kind of how physics works, though, isn't it? Like, we make measurements on reality, and we make conclusions from that. We draw conclusions from those observations. We make predictions and then go make further observations to see if we confirm them to figure out how reality works. I almost feel like Dr. Craig is like shoehorning this concept of verificationism into special relativity, seemingly unjustifiably. I haven't heard any actual argument for why we should assume that that was ever the case, just so that he can have grounds for rejecting the conclusions that it's reached. Oh, well, special relativity, I reject its conclusions. It's just verificationist in nature. It works on this operational definition of science and, an understanding of what reality is. And so it makes a bunch of presuppositions that I don't like. I really don't want to sound rude saying this, but I would wonder how much of like the actual history of special relativity that Dr. Craig has read, because I've just spent the last 2 days reading it, and none of what he's saying is what at least I got out of what was written down, and a lot of what I read was at least what we can find about what Albert Einstein himself said about a lot of what was going on at this time. What he said about, Lorentz's electron theory, what he said about electromagnetism, what he said about the principle of relativity, what he said about his own thought experiments, like the one that he performed at the age of 16, where he imagined himself riding on a light wave and then wondered, what would happen if I looked over at another light wave? I would see that light not moving at all, which seems to reject all of the conclusions did um, clash greatly with the conclusions of electromagnetism of the time, which did give the speed of light would be constant. And if the speed of light is constant, it's always traveling at that speed. How can you look over and see light not traveling at all? You would just see sort of a static electromagnetic wave, which is not something that electromagnetism tells us can be the case. And physicists still haven't, I don't think, really resolved this thought experiment. I'd have to look, and I didn't look into specifically that thought experiment that deeply, but to me, it is a very, very interesting thought experiment. But this seeming shoehorning of the concept of verificationism into special relativity as justification for rejecting it, I don't really like that. Based off of what I've been reading over the last 2 days, does not seem to be a proper representation of how Einstein or any of the great minds, Poincaré, Lorentz, because they made some contributions, they developed things that Einstein himself used. This doesn't seem to be something that any of them were doing. What he's saying does not seem to be present in their thoughts or in their work when they were developing this.
Time and space, which transcend operational definitions, are implied to be mere figments of our imagination. In Einstein's other early papers on relativity, his verificationist theory of meaning comes even more explicitly to the fore. Concepts which cannot be given empirical content and assertions which cannot be empirically verified in principle are discarded as meaningless. In his article, in the Jahrbuch der Radioaktivität und Elektronik of 1907, after giving his operational definitions for time and simultaneity, he asserts that to refer to the time of an event without reference to its inertial frame has no sense, Sinn. In his piece in the Physikalische Zeitschrift of 1909, he asserts that statements about the time of an event have no meaning, Bedeutung, unless one refers to clocks at rest in the relevant inertial system. In his summary paper, the Relativitätstheorie, published in 1911, Einstein expresses himself at greater length concerning the meaning of statements about time and space. He says, and I think I have a quotation of this. No. He says, in order to arrive at time specifications of a very precise sense, we use a prescription that relates to clocks, which are relative to a certain coordinate system K. We have not gained simply a time, he says, but a time relative to a coordinate system. Quote, it is not said that time has an absolute meaning. That is an arbitrary element which was contained in our kinematics. We then come, Einstein proceeds, to the second arbitrary element in kinematics, the absolute length of a body. Quote, we now ask, how long is this rod? This question can only have the meaning, what experiments must we carry out in order to discern how long the rod is, end quote. Einstein then proceeds to describe length measurements of a moving rod by means of synchronized clocks. By abandoning the presuppositions of absolute time and space and substituting in their stead operational definitions, Einstein reduces time and space to our measurements of them. He concludes, quote, since we have...
Again, though, that's what physics is. We make measurements of things and we use those to define what they are and how they behave. That's kind of the whole point of like physics and physical science. So yes, space and time are nothing more really than how we measure them. And the thing is, we've even confirmed that these are things like length contraction and time dilation are physical effects that occur. And by saying that, oh, well, no, it's only results of our measurement, we can't ever falsify that because we can only rely on our measurements to understand what's going on. So the very concept of lengths and times only being reduced to our measurements can't be falsified, because in order to do that, we have to make measurements of length and time. And when we do that, we get relativistic results. He is correct, though, that it makes no sense to define a length without reference to some other coordinate system. It makes no sense to reference some other time without reference to some other coordinate system. And when you change or transform between coordinate systems, what you find is that lengths can get shorter, at least in the direction of travel, and the time elapsed on any clock can dilate or get longer. And we definitely have measured these effects, but essentially the proposition that he's giving is that, oh, well, these are just results of our measurements. How could we ever falsify that? Because we could only ever falsify it through making measurements. So it's just an unfalsifiable claim about space and time, about physics, that seems to just ignore the fact that the whole of physical science is about making measurements on reality and deducing from it how it behaves. And that's exactly what special relativity aids us in doing, and that's exactly how it was developed. And that is why, I mean, we can just apply Occam's razor here. Why presume that there is an absolute time and that we have absolutely no way of measuring it, and that reality doesn't seem to behave as if there is one, instead of just assuming that there isn't really an absolute space and time, and those are just relativistic concepts.
In a precise way, physically defined coordinates and time, every relation between spatial and temporal entities will have a very precise physical content, end quote. Statements about spatial or temporal relations, which are metaphysical in character, that is, are independent of clocks, rods, and reference frames, are nonsense. It is frequently asserted that as Einstein labored on the general theory, he came to see the bankruptcy of Mach's positivism. But this claim needs to be carefully qualified. What Einstein's work on GTR, in fact, revealed to him was the inadequacy of Mach's phenomenalism. Scientific theorizing is not the mere linking of observation statements, but involves a creative exercise of the mind, which is free to postulate theoretical entities not directly given an observation. Nevertheless, even after GTR, he continued to regard such theoretical terms as meaningless unless they could somehow be linked to observation statements. In 1920, for example, he writes, "We thus require a definition of simultaneity such that this definition supplies us with the means by which, in the present case, he can decide by experiment whether the lightning strokes occurred simultaneously. As long as this requirement is not satisfied, I allow myself to be deceived as a physicist. And of course, the same applies if I am not a physicist, when I imagine that I am able to attach a meaning to the statement of simultaneity. For physicists and non-physicists alike, the statement that two events occur simultaneously is meaningless unless an operational definition can be given for that concept. Thus, he continued to cling to his rejection of metaphysical space and time. He says, the only justification for our concepts and system of concepts is that they serve to represent the complex of our experiences. Beyond this, they have no legitimacy. I am convinced that the philosophers have had a harmful effect upon the progress of scientific thinking in removing certain fundamental concepts from the domain of empiricism, where they are under our control, to the intangible heights of the a priori. For even if it should appear that the universe of ideas cannot be deduced from experience by logical means, but is, in a sense, a creation of the human mind, without which no science is possible, nevertheless, this universe of ideas is just as little independent of the nature of our experiences as clothes are of the form of the human body. This is particularly true of our concepts of time and space, which physicists have been obliged by the facts to bring down from the Olympus of the a priori, to adjust them and put them in a serviceable condition. Einstein's theory, far from disproving the existence of absolute space, actually presupposes its non-existence. All of this is done by mere stipulation. Reality is
not really. Reality behaved through observations of electromagnetism in a way in which you would expect if space and time were not absolute things. This is why the Lorentz transformations, which give length contraction and time dilation, which themselves show that time and space aren't really absolute things, had to be used in order to make electromagnetism work. We got no accurate results if we assumed an absolute space and time. Time and space had to be relative to make sense of that, and that has been further confirmed through quantum electrodynamics, which is a relativistic quantum field theory, and that does not work if you assume absolute space and time. The whole thing would fall apart. So this is just the way that reality behaves.
reduced to what our measurements read. Newton's metaphysical time and space, which transcend operational definitions, are implied to be mere figments of our imagination. How then shall we assess the claim that STR has eliminated absolute time and space? Well, the first thing that needs to be said is that the verification.
Honestly, I think the easiest way to show that there is an absolute time and space would be to give a universal spatio-temporal frame of reference that physicists can work with. And that boom, that is just proven that there is an absolute space-time, or at least an absolute frame of reference for space-time. Nobody's ever done that. I mean, physicists tried. They were trying to maintain this notion of absolute space-time and everything that we were learning from electromagnetism by proposing an ether. They failed miserably. Well, I shouldn't say miserably, but they failed. And Einstein came along and showed, no, we don't need this notion of absolute space and time, nor do we need this idea of an ether that is this fixed and immutable thing to explain the phenomena that we see in realities, primarily through electromagnetism. All we need is that space and time are dynamical rather than these static and absolute things. They are dynamical. And the thing is, general relativity also tells us that too. And I don't know what it would mean to curve an absolute space and time. So we haven't gotten to general relativity yet, though. But yeah, this consistent shoehorning of the idea of presuppositions of the relativity of space and time and of simultaneity into special relativity. I'm sorry, that's just not the case. And anybody can go for themselves and read the literature that is out there on how special relativity was developed, because this was more than just Einstein. Now, Einstein was the one that really took all the concepts and put them together and was capable of pulling out the full picture. But there were other men that contributed to this. James Clerk Maxwell, Henry Poincaré, Heinrich Lorentz. These men contributed to the development of this. And Einstein used a lot of their ideas. And many of these men came to accept special relativity when Einstein released it, as most of the physics community did, and eventually all of the physics community did. There was no presupposing that there isn't an absolute space and time. What we did is we went out, started measuring reality, started developing theories about it, and under the presupposition that space and time were absolute, reality didn't seem to make a lot of sense. What we were looking at and what we were observing is not what we should be seeing. And then here comes a bunch of men who have this idea. They take the principle of relativity, they apply it into electromagnetism, they give all these relativistic-like effects, and then Einstein comes along and really formalizes those, shows that there's really no such thing as simultaneity. And the big thing was absolutely nothing in electromagnetism had to be modified to get special relativity to work, or to keep electromagnetism intact under special relativity. Nothing had to be changed. They went together beautifully. And most physicists will tell you this. something like special relativity just falls out of electromagnetism. And going even further, excuse me, we can see these effects in other forces outside of electromagnetism, strong interactions. We can see these effects in strong interactions. Gluons travel at sea. They're massless particles. There are relativistic effects in strong interactions. There are things that there are symmetries that are hard to preserve or conserve if you don't assume relativistic effects. Reality just doesn't work this. If there truly was an absolute space in time, I think physicists would know by now. And just another point to this notion of absolute space and time that I think hurts it as well is that space time might not even be a fundamental aspect of reality. Time, potentially, yes. Space, a lot of physicists now are saying it doesn't look like space as this manifold is a fundamental aspect of reality. Time could be, maybe it isn't, but space does not look like it is. How could these things be absolute if they're not even fundamental to reality? It seems that their absoluteness would necessitate their being fundamental to reality, but if they're not, I don't know how they could be absolute. See, it's not just that we've demonstrated these things with merely special relativity. It's not that we made a bunch of presuppositions and baseless assumptions working from a verificationist perspective, and this got special relativity. It's that we started developing models of reality, and special relativity fell out of them. And as we continued to examine reality more fundamentally, we continued to confirm those very effects, those very results. So I definitely think Dr. Craig has a large uphill battle here if he's planning on overturning special relativity and what would fall from that general relativity.
Verificationism, which characterized Einstein's original formulation of STR, belongs essentially to the philosophical foundations of the theory. The whole theory rests upon Einstein's redefinition of simultaneity in terms of clock synchronization via light signals. But that redefinition assumes necessarily that the time which light takes to travel between two relatively stationary observers, A and B, is the same from A to B as from B to A in a round-trip journey.
Well, yeah, and that's the problem with this whole one-way, two-way speed of light thing that you hear all the time is that we have ways of measuring what the speed of light is independent of like sort of, and I'm being a little bit like obviously a bit facetious with this, but it's not like we can the only way to do it is to sort of take a speed gun, point it at a photon, and measure how fast it goes. The speed of light was deduced from initially from Maxwell's equations, and it lined up with the observations that we did make on the speed of light at the time, about 186,000 miles per second. The speed of light now is generally given by the equation 1 or the square root of 1 over epsilon naught mu naught, which are two constants that essentially help us to understand and define the structure of an electromagnetic field in the bare vacuum of spacetime. And that if you perturb it with, say, electromagnetic radiation, you will get a particular velocity at which that radiation propagates through the field, and that's 2.9979245 times 10 to the 8th meters per second, the speed of light. There are also other things that also travel at this. Are we assuming that that gluons only travel at that speed in one way? Is that just an assumption, or both ways? Is that just an assumption we're making? How come gluons behave exactly the same way as photons do? What would constrain both photons and gluons to this? Well, we're assuming that their two-way speed is the same as their one-way speed. Why? We say that about photons. What's constraining gluons is the same way. If photons behave differently in a one-way direction than in a two-way direction, shouldn't we expect the same for gluons? We never hear them mention gluons when it comes to the speed of light. And that's because I think a lot of them think, and I don't know what gluons are the particles that mediate strong interactions. They are to the strong nuclear force what photons are to electromagnetism. They carry the force. What was I going to say? Shit, I lost it. Anyway, let's continue. He keeps. There was something I wanted to say as to the relativity of simultaneity, and I can't remember what that was. Well, I suppose the relativity of simultaneity has, by all rights, been observed. Einstein, that came to Einstein, number one, as a way of maintaining the principle of relativity, which he thought was better to preserve than the concept of an ether. But he sat there and thought about what you would do if you took somebody standing next to train tracks with a tree at 60 kilometers in either direction from them, and somebody that was standing on a train going down the tracks. And when both the people are lined up, so if you could look at like the person traveling on the train and then you have the person stationary, when they're right next to each other, two flashes of lightning strike both the trees. The person standing there, what would he see? Well, he would probably see them simultaneously. But what now about the person who's traveling on the train? What would he see? Well, he's moving in a direction. There's motion to what he's doing. And we already know that motion, we can't define the concept of absolute motion. That's essentially what the principle of relativity, which has been around since before Einstein, and who Einstein, or since before Newton, and that which Newton did not overturn at all. In fact, it's incorporated into his equations of motion explicitly, the principle of relativity. We would know that since this person is in motion, they would see the flash of lightning that is in the direction of their motion just slightly before the flash of lightning that is in the direction away from their motion. The concept of two events in spacetime being simultaneous does, I would think, obviously depend on the coordinates you're using to measure the events. And ultimately, what relativity, both special and general, tells us is that more so special, but these concepts certainly exist in general relativity, is that measuring anything, the length of something, how fast it's moving, the direction in which it's moving, its orientation, the amount of time elapsed on its clock, all of those things are relative to the coordinates you use to measure against it. And so there could be two coordinate systems in which an event appears simultaneous, and a third one in which it doesn't appear simultaneous, in which two events don't appear simultaneous. And these things have been experimentally confirmed, I think, in more than one way.
That assumption presupposes that A and B are not both in absolute motion, though relatively stationary with respect to each other. Or in other words, that absolute space nor a privileged reference frame exists. The only justification for that assumption is that it is empirically impossible to distinguish uniform motion from rest relative to such a frame. And if absolute space and absolute motion or rest are undetectable empirically, therefore they do not exist, and may even be said to be meaningless.
Well, it's not. I mean, they don't exist, but that is assumed from the fact that we can't empirically measure. We can't empirically measure ferries that are actually pushing the photons around that gives rise to the electromagnetic force, even though we don't even need those to explain what we see. We haven't empirically measured them either. I wonder if Dr. Craig would be willing to say that thereby it is reasonable to presume that maybe there are actual little electromagnetic ferries that push the photons around that give rise to the force, even though we've never empirically measured them and they do nothing to add any explicative power to our models. And in fact, most physicists would say confound with a lot of what we know about physics, that, it isn't the result of little fairies doing things. The fact that we can't empirically measure anything like an absolute space, absolute time, or absolute motion is evidence that that it isn't a meaningful concept. That isn't assumed. It's because in physics, if we can't measure something, if it's not a part of our equations, if it doesn't appear as if reality operates that way, then it is assumed. I would actually say presumed that it probably isn't real. We utilize Occam's razor for that. It's the same reason that we don't make this presumption, or we don't have this idea that there are literally electromagnetic fairies pushing the photons around. We don't need them to explain what electromagnetism is. Number one, we don't need absolute space and time to explain how reality works. Number two, we've never seen them, just like we've never measured absolute space or time or motion. And number three, they actually seem to directly confound with what we do measure. Taking all of these together, I think one is, and scientists are certainly epistemically justified in saying these things probably aren't real. If they are, show us an absolute spatiotemporal frame of reference in which you've defined absolute motion.
But if verificationism belongs essentially to the foundations of STR, the next thing to be said is that verification...
Essentially, verificationism is it is the root of science. Physical, empirical sciences utilize a verificationist perspective. If we can't empirically demonstrate it, it doesn't matter to us. It's not a thing that we're going to put in our models. So, sure, most physicists might say, sure, you can say that even though we can't ever measure it, we don't need it to explain anything. It confounds with our equations and what observations we have made. If you want to assume that there still is an absolute space-time and an absolute motion and absolute frames of reference, go right ahead. But we're not going to use them because we've never seen them, we've never measured them, we've never detected them, and we don't need them to explain the reality that we see, which are all things that we would expect if there was no such thing as absolute space, absolute time, or absolute motion. An idea, at least with motion, that has been around since before Newton and that Newton's equations of motion thoroughly enjoy.
Has proved to be completely untenable and is now obsolete. The untenability of verificationism is so universally acknowledged that it will not be necessary to rehearse the objections against it.
Well, yeah, I mean, verificationism isn't going to get you very far if you're having a discussion on like morality or epistemology or certain things like that. But in science, verificationism, and I don't think verification is solely the thing that is used in science, but I do think that with the empirical sciences, like the physical sciences, like physics, verificationism is a large part of that. Look, if we can't empirically demonstrate that this thing is here, it has behaviors, it has properties that we can measure, we can define it through equations of motion, then what do you expect when physicists say that they're not going to consider it? That's literally how physics works.
Here, verificationism provides no justification for thinking that Newton erred, for example, in holding that God exists in a time which exists independently of our physical measures of it and which may or may not be accurately registered by them.
Also, if Dr. Craig is going to postulate that there is an absolute space and time and an absolute motion that you could define in it, but there's just no way for us to really measure it, then he's again making a statement about something that's there that's just unfalsifiable. And I can assure you, physicists aren't going to consider something if it's unfalsifiable. That's part of the reason that certain things that Dr. Craig himself doesn't like, and he's made this same exact argument against them, like the multiverse theory. Or multiverse hypotheses, rather. The vast majority of them are unfalsifiable. And so science isn't going to consider them for that fact alone. Because if they're unfalsifiable, if there isn't any possible way to empirically demonstrate it, then we can't make any statements that it has any effect in our reality. And it probably doesn't, because if it did, we should be able to measure that. And if we can't, then its effect would be so minimal that it wouldn't actually have much of an effect. And so again, we see with Occam's razor, we can just shave it away. It has no utility. So it's funny that Dr. Craig would appeal to the unfalsifiability of certain models when it favors his position, but then when it doesn't, it seems that he wants to present unfalsifiable models against, or objections that are ultimately unfalsifiable against the models he doesn't like.
It matters not a whit whether we finite creatures know what time it is in God's absolute time. God knows, and that is enough. Now, I am not here endorsing Newton's view on divine eternity, but I am saying that the natural theologian who, like Newton, believes God to be temporal need not be fazed by STR. because STR's claim that absolute time does not exist is founded essentially upon a defunct and untenable epistemology.
No, it's not. Also, verificationism as a broad epistemology, yeah, most epistemologists are probably going to be disfavorable to it. But within specifically the empirical sciences, of which we've got physics and chemistry and biology, and there are others that are fairly empirical, but if we're talking like the most empirical sciences, it's physics and chemistry. They are going to operate from a verificationist perspective. Essentially, that if we cannot empirically verify the action or interaction of something with the physical world, or the extent of something in the physical world, we don't have the capability of making any statements about what it is or what it isn't. It's meaningless to us. Any physicist, I think, worth their salt at least, would tell Dr. Craig this, given how often he at least claims to talk to physicists. I would venture to guess this may have been told to him. Either, if it hasn't, I would assume it's either due to the fact that he's not talking to as many as you may want people to assume, or the ones that he is talking to just have their own personal biases, which may potentially align with Dr. Craig's. But I don't think verificationism is entirely what the physical sciences are rested upon, though I would say that it is a large part of it. And I don't think that epistemologists would say that it shouldn't be, or that it's not justified that the physical sciences, the empirical sciences, work from a verificationist perspective.
If we do suppose that God is in time, then how should we understand STR? Henri Poincaré, the great French mathematician and precursor of STR, helped to point the way. In a fascinating passage in his essay, The Measure of Time, Poincaré briefly entertains the hypothesis of an infinite intelligence.
So, just really quickly, just to really summarize what it is exactly that Dr. Craig is really saying there with this whole verificationism, special relativity is dependent on it, it's a defunct epistemology, is he's essentially saying that the empirical measurements we've made on reality and the fact that they've never returned anything that resembles an absolute temporal or spatial frame of reference or anything like absolute motion isn't enough to say that those aren't features of reality. And I have to be honest, I think that it is. I think that we are, as a species and as scientists, which wouldn't include me. I'm not really a scientist. I just like science. That we are justified epistemically in concluding that they're not real because we haven't been capable of empirically confirming them. And what we have been capable of empirically confirming confounds with the idea of them being real. Reality does not operate the way you would expect if there was an absolute space and time.
Une intelligence infinie, and considers the implications of such a hypothesis. Poincaré is reflecting upon the problem of how we can apply one and the same measure of time to spatially distant events. What does it mean, for example, to say that two thoughts in two people's minds occur simultaneously? Or what does it mean to say?
Also, now that he just brought it up, there was something I wanted to mention that I completely spaced earlier. He said earlier in the video that, well, Einstein just reduces the concept of simultaneity to a synchronization of clocks. If they're not synchronized in two events, or if they're not reading the exact same time, and if the time coordinates, so to speak, for two events in space-time does not overlap, then they're not simultaneous. But my question is for Dr. Craig, well, if we're not using a concept like that, what does it mean for two things to be that's what simultaneous means, occur at the same time. So of course, if the time coordinates for two events do not overlap, we wouldn't say they're simultaneous. Overlapping temporal coordinates is what it means for things to be simultaneous. Unless he's got a better definition, perhaps he has. I'm not having a discussion with him. I don't know. I would doubt it.
That a supernova occurred before Columbus saw the New World. Like a good verificationist, Poincaré says, and I quote, all these affirmations have by themselves no meaning. Then he remarks, we should first ask ourselves how one could have had the idea of putting into the same frame so many worlds impenetrable to one another. We should like to represent to ourselves the external universe, and only by so doing could we feel that we understood it. We know that we can never attain this representation. Our weakness is too great. But at least we desire the ability to conceive an infinite intelligence for which this representation could be possible, a sort of great consciousness which should see all and which should classify all in its time as we classify in our time the little we see. This hypothesis is indeed crude and incomplete, because this supreme intelligence would be only a demigod. Infinite in one sense, it would be limited in another, since it would have only an imperfect recollection of the past. It could have no other, since otherwise all recollections would be equally present to it, and for it there would be no time. And yet, when we speak of time, for all which happens outside of us, do we not unconsciously adopt this hypothesis? Do we not put ourselves in the place of this imperfect God? And do not even the atheists put themselves in the place where God would be if he existed? What I have just said shows us perhaps why we have tried to put all physical phenomena into the same frame. But that cannot pass for a definition of simultaneity, since this hypothetical intelligence, even if it existed, would be for us impenetrable. It is therefore necessary to seek something else. Poincaré here suggests that,
I'm sorry, I have to pause this and like read that because he speaks it so slowly, which he's presenting to a crowd. We should first ask ourselves how one could have had the idea of putting it in the same. We should like to represent ourselves. Yeah, this I don't really see how what. Well, let me listen to what he has to say about it.
that in considering the notion of simultaneity, we instinctively put ourselves in the place of God and classify events as past, present, or future according to his time. Poincaré does
I'd be curious to know what God's time is. Is he in the past? Is he in the present? Is he in the future?
not deny that from God's perspective, there would exist relations of absolute simultaneity. But he rejects the hypothesis as yielding a definition of simultaneity because we could not know such relations. Such knowledge would remain the exclusive possession of God himself. Clearly, Poincaré's misgivings are relevant to a definition of simultaneity only if one is presupposing some sort of verificationist theory of meaning, as he undoubtedly was. The fact remains that God knows the absolute simultaneity of events, even if we grope in total darkness. Nor need we be concerned with Poincaré's worry that such an infinite intelligence would be a mere demigod, since there is no reason to think that a temporal being cannot have a perfect recollection of the past. There is no conceptual difficulty in the idea of a being which knows all past tense truth.
How are we defining past? How are we defining present? How are we defining future?
His knowledge would be constantly changing as more and more events become past. But at each successive moment, he could know every past tense truth that there is at that moment. Hence, it does not follow that if God is temporal, He cannot have perfect recollection of the past. Poincaré's hypothesis suggests, therefore, that if God is temporal, his present is constitutive of relations of absolute simultaneity. Compare H.A. Lorentz's illustration of a world spirit, or Welt.
Oh, wait, so Dr. Craig appears to be saying that, oh, well, I mean, things are absolutely simultaneous with respect to God's frame of reference, which assumes that there is a God that exists.
Geist, in his letter to Einstein in January of 1915, in words redolent of the general scholium and optics of Newton, Lorentz broached considerations whereby, he said, I cross the borderland of physics. He wrote, a world spirit who, not being bound to a specific place, permeated the entire system under consideration, or in whom this system existed, and who could feel immediately all events, would naturally distinguish at once one of the systems, U prime, etc., above all the others. Such a being, says Lorentz, could directly verify simultaneity.
Yes, I don't think a lot of people would disagree with this idea that if God existed and he had some absolute frame of reference for space-time, then from his frame of reference we could define moments being simultaneous. But this isn't going to work for most physics and physicists who don't see God anywhere in the equations or in reality. If God is in space-time, then the question becomes, at what points, at what coordinates in space-time is he located? And it seems to me that if he's located in space-time, which seems to be the case here, and that, well, thereby his frame of reference would be absolute. If he's in space-time, then in what way is his frame of reference absolute? It's just another frame of reference in space-time. How would that make it, how would it being God's make it privileged? And if God is not in space-time, then how do you differentiate him from existing and not being in space-time and not existing at all?
On this view, the philosopher J.N. Findlay was wrong when he said, the influence which harmonizes and connects all the world lines is not God, not any featureless, inert medium, but that living, active interchange called light, offspring of heaven, firstborn. On the contrary, the use of light signals to establish clock synchrony would be a convention which finite and ignorant creatures have been obliged to adopt. But the living and active God, who knows all, would not be so dependent. In God's temporal experience, there would be a moment which would be present in absolute time, whether or not it were registered by any clock time. He would know without any dependence on clock synchronization procedures or any physical operations at all, which events were simultaneously present in absolute time. He would know this simply in virtue of his knowing at every such moment the unique class of present tense truths at that moment, without any need of physical observation of the universe. So, what would become of STR if God is in time? From what has been said, God's existence.
So we're about a little over halfway through the video. Just to do a quick recap, I can see there's some new faces in here in the side chat. But I also want to, I'm interested how many other people caught this as well. Essentially, what Dr. Craig has done in this discussion is shoehorn this concept of verificationism as being the only foundation of special relativity. And, oh, well, epistemologists don't like verificationism. It's primarily outside of the realms of empirical science. Therefore, it's founded on faulty premises, and just the empirical measurements we make on space and time that don't return any absolute notions with respect to it doesn't mean that they're not there. And then says, okay, so we don't really need to worry about what special relativity says because of the presuppositions that it makes, and then presupposes that we can rescue these notions of absoluteness in regards to space and time and causality and simultaneity and motion if we just presuppose that there's a God and that his his frame of reference is the privileged one. So he's knocking special relativity because it makes presuppositions that he doesn't like, and then is replacing it with a presupposition, i.e. God's existence. That is what has happened here. That is what has happened. And it's interesting because the main reason that Dr. Craig does not like special relativity is because it shows that simultaneity is not absolute. And thereby, something that's very important to him in the Kalam cosmological argument is that God's creation of time is simultaneous with time's coming into being. But if no two events can be, so essentially God's creation of time, it's a creation of time that is in time, since time's existence is simultaneous with God's decision to create it. He proposes this because it rescues the idea that you can't create really without the notion of time, and you need to be in time in order to create it. But if those two events were simultaneous, then the problem is solved. But if God's creation of time is in time because it's simultaneous with time coming into existence, and time does not have the property of absolute simultaneity, then with respect to what is God's creation of time simultaneous with it coming into existence? That's one. The second one is that special relativity, and thereby these time dilation effects that Dr. Craig desperately seems to want to get around, would show that presentism seems to be false. And if presentism is false, then his construction of the Kalam cosmological argument falls apart. So his rejection of special relativity is really centered around protecting the Kalam cosmological argument, which is an argument for God's existence. Now, notice here that he is rejecting special relativity on the presupposition of God's existence to then rescue the Kalam cosmological argument to argue for God's existence. Which means that if you take what he's saying here and you tie it with other things that he said about the Kalam, he's arguing in one giant ass circle. He's presupposing God's existence to argue for God's existence. That, Dr. Craig, is logically fallacious.
In time would imply that H.A. Lorentz, rather than Einstein, had the correct physical interpretation of the mathematical core of relativity theory. That is to say, Einstein's clock synchronization procedure would be valid only in the preferred or absolute reference frame, and measuring rods would contract and clocks slow down in the customary special relativistic way when in motion relative to the preferred frame.
No, that's not what is true in special relativity, because there are no preferred frames of reference in special relativity. So what you can do is take an ideal frame of reference that you can just treat as being not being under any relativistic effects, which means your x and y axes, or rather your x axis representing space and your t axis representing time, would just be they would be what's called normal to one another, or perfectly perpendicular, 90 degrees between them. As you begin to approach the speed of light, those axes converge on each other. The speed of light can be drawn as a line coming out as a 45-degree angle from the origin. That is called a space-time diagram. All the other lines that are perpendicular, or parallel rather, to the y-axis or your t-axis move as it moves, and likewise with the lines in space. So what this means is that when you transform from an inertial reference frame to a relativistic or an at-rest reference frame, which I think that's an inertial reference frame, a reference frame treated as if it's at rest, to a relativistic reference frame, coordinates will move. Lengths will contract, time will dilate. So there is no real preferred frame of reference, but you can take an inertial frame of reference and treat the axes as at 90 degrees to one another, and thereby under no inertial effects. But that doesn't actually mean that that would represent your frame. Everybody measures their own reference frame as an inertial one. If you were traveling at 100,000 miles per second, about 85-ish percent, 85% the speed of light, you would still measure your own clock passing at 1 second per second. It's only when you go from an inertial frame into a relativistic frame that you notice the effects. So it is against some other coordinate basis that you measure the relativistic effects. It doesn't there doesn't need to be some unique preferred coordinate basis in order to measure any of these effects. It's just measuring them from one coordinate basis to the other. You will notice changes in lengths, in amounts of time elapsed, and a variety of other things. Well, not really a variety of other things other than differences in where the coordinates are actually mapped graphically. And we can represent these. These are represented as length contraction and time dilation. In fact, these kinds of transformations had to be performed before special relativity was developed, as I mentioned earlier. The Galilean transformations did not work. So Heinrich Lorentz, the very person he's talking about now, introduced a set of transformations that did work called the Lorentz transformations. And that is where we get the concepts of length contraction and time dilation from. And again, those coordinate transformations have been around since before special relativity. They came from electromagnetism, as special relativity did, and Einstein used them to redefine space-time intervals in a space-time. And that it gave rise to these length contraction and time dilation effects of objects moving at very, very high speeds.
Such an interpretation would be implied by divine temporality. For God, in the now of absolute time, would know which events in the universe are now being created by him and are therefore absolutely simultaneous with each other and with his now. This startling conclusion shows that Newton's theistic hypothesis is not some idle speculation, but has important implications for our understanding of how the world is.
I don't think that Newton's conception of absolute space and absolute time are intrinsically theistic. I think that he incorporated those concepts into his theistic belief system, is as sort of arguing that God grounds absolute space and absolute time, but one needn't consider them necessarily within a theistic context to use them. And physicists did use them because classically, when we're not considering relativistic effects, it seems that that's the way space and time are. And then we started developing electricity and magnetism, and you got various effects. So just to give an example of something that's very, very odd, something that Einstein himself considered in looking at electromagnetism and then eventually working special relativity out of it, was the idea of a magnet. If you took a magnet and you accelerated it, it was believed that because, again, these effects were supposed to propagate through the ether, because how else do they propagate their waves? Waves require a medium. There must be a medium for light and for all electromagnetic phenomena, in fact. But and these effects, we know that an ether doesn't exist now, but these effects are still real, and they have to do just with their relativistic effects of the electromagnetic field as defined by relativistic quantum electrodynamics. If you take a magnet and you start moving it through space, it will create an electric current. If you are moving with the magnet, you will not observe an electric current because you're moving with the magnet. It was believed that, well, then if you're stationary and you watch a magnet go by, you should see an electric current in it. We just have to put a conductor around it to be able to measure that electric current. And let's do that and see what happens. And anybody that knows anything about, I think it's the Lorentz force factor, Lorentz, something like that. The conductor will also, since it is in a magnetic field and it is moving and so is the magnetic field, that electric conductor or that conductor will create its own electric field, as will the magnet. The magnet will create its own and the conductor will create its own, and they will cancel each other out. And so you do not, even if you were to look at a magnet moving, you wouldn't necessarily, well, I mean, there is an electric charge there, but you wouldn't actually measure one. And so what Einstein said about this is that, well, so it seems that electromagnetism is telling us, well, you've got to have a medium for the electromagnetic force to be propagated through. That's the ether. But if you take the truth of the theory and try to measure that ether, you're never going to be able to measure it. The very thing that electromagnetism seemed to rely on was itself unfalsifiable, utilizing any measurements of electromagnetism, which seems interesting. Einstein said there's got to be something off here. One of two things must be true, and I did mention this a while ago. A, there is no ether. B, the principle of relativity is false. Well, if the principle of relativity is false, these kinds of effects we shouldn't see. The fact that we see them seems to conform with the principle of relativity, so I'll keep that. And he got rid of the ether and eventually developed special relativity. And then Hermann Minkowski came along and actually put space and time together, because the equations that Einstein was using to define, as he put it, the electrodynamics of moving bodies, treated space and time that way. And Hermann Minkowski said, well, look, we can just take what you said, put them together into a four-dimensional manifold. There isn't an ether. There's just a four-dimensional manifold, and the electromagnetic radiation can propagate through that because the electromagnetic field is present at every point within it. So we don't need an ether. We have space-time. It is dynamic. Length contraction and time dilation are real effects. We've measured them. And simply saying that because we can empirically measure them does not mean that there isn't still potentially an absolute space and time. It's just positing unfalsifiable assumptions that we don't need. They don't add any explicative power to reality. So utilizing Occam's razor, we can shave them away. I must be honest, we're a little over halfway through this, and I don't think that Dr. Craig has presented a very convincing argument.
And for the assessment of rival scientific theories. Lorentzian relativity is admitted on all sides to be at least empirically equivalent to Einsteinian relativity. And there are even indications on the cutting edge of physics today that a Lorentzian view may be preferable in light of recent discoveries.
So this video is from 2012. What he said is actually not true. You'll notice that nobody is using Lorentzian relativity. It is true that a neo-Lorentzian framework that posits some sort of, immutable, undetectable, unfalsifiable ether is empirically similar to special relativity. However, it convolutes things. It complicates things a little bit. You have to require more assumptions, like, an ether that is unnecessary, and certain things in special relativity, like the constancy of the speed of light, fall out of special relativity more naturally than they do in neo-Lorentzian framework. And again, we don't. The biggest thing with most physicists is that, sure, yeah, you can make them empirically equivalent, but why would we take the one that, in order to get the same empirical equivalency as the other, has to have more assumptions, like some undetectable, unfalsifiable ether? Again, we can use Occam's razor, and William Lane Craig on a number of occasions has appealed to Occam's razor. We can utilize that to shave away this concept of the ether, and we see that we have rescued special relativity as a superior framework because it explains everything that we'd like to explain. It does so a little bit more simply, and it does so with less assumptions.
In fact, due to developments in quantum physics, there has been what one participant in the debate has called a sea change in the attitude of the physics community toward Lorentzian relativity.
I can assure you that is false. Relativistic quantum field theory does not utilize a Lorentzian framework. Another issue with the Lorentzian framework is that we don't know how to derive what would be its equivalent of general relativity, or a description of gravity, which is another reason why general relativity sort of just falls naturally out of special relativity. If you just take special relativity and apply it to curved spacetimes or irregular manifolds, you get what we call general relativity. You can't really just do the same with a Lorentzian framework, which is another reason why a lot of pretty much all physicists and philosophers of physics as well don't have any preference toward it. And there is no growing preference. I can assure you that.
Again, none
As could any physicist if you didn't want to take my word for it.
of this proves that Newton was right in thinking that God is in time. But it does undercut the claim that STR has proven Newton to be wrong. The defender of divine temporality can plausibly reject the first premise of the argument for divine timelessness based on the special theory of relativity. In conclusion, relativity theory does not provide good grounds for thinking that God is timeless. The Einsteinian interpretation of STR is based essentially upon an untenable and obsolete verificationist epistemology.
No, we went over that a couple of times already. It's not. I mean, unless Dr. Craig is saying that when we're doing physics, we shouldn't go with what our empirical measurements are telling us about how reality is behaving, because I don't like the conclusions of it. Which is essentially what he's saying there. Oh, well, it's just verificationist. It presumes that there is no absolute space and time, and then it makes measurements that, show that if when we measure things in space and times, there is no such thing. There are no preferred frames of reference. There is no absolute motion. There is no, absolute simultaneity, things like that. Well, not really. It's just that that's the way we observe reality behaving. Reality behaves as if there is no absolute spatio-temporal frame of reference. Reality behaves as if there is no absolute simultaneity. Reality behaves as if there is no absolute motion. Again, what he's saying is that the empirical measurements of physical reality aren't enough to rule out particular ways for how it operates, especially when the only empirical measurements we've ever made on reality give only one type of way that it operates, and that's not an absolute space and time. I am just not at all convinced by this. Again, shoehorning of verificationism into special relativity.
And so cannot force abandonment of the classical concept of absolute time, which is constituted by God's duration. Moreover, GTR, in its cosmological application, furnishes us with a cosmic time parameter, which may be plausibly interpreted as the appropriate measure of God's time since the moment of creation.
So just to touch on that again, cosmic time is entirely arbitrary. It is what we do when it is synonymous with age of the universe. If we took a clock and we isolated it so that there were no time dilation effects on it, so it's just an ideal scenario, because that you could never really actually do that, but there are no time dilation effects on this clock, and when we go back as far as we are capable of going with our physical models, we set the clock to 0 and we just let it tick at 1 second per second with no time dilation effects. What time do we get? 13.8 billion years roughly. And so we use that as an arbitrary yardstick essentially for measuring time on cosmological scales. We measure it against cosmic time. But again, that's entirely arbitrary to human beings. So he's essentially saying that God's time is arbitrarily decided by humans in terms of what's conventionally useful for how we make measurements and develop physical models about reality, which is, I don't think, something that Dr. Craig would really like to say.
Thank you.
So that's the end of the presentation. I'm going to let it go. I don't know if there's a Q&A. If there is, I probably won't watch that, just because I might do a few questions just to see if it's interesting, but otherwise I'll probably end the stream if I'm not interested in what comes here after.
Two things before we start the Q&A. First,
Okay, so there is a Q&A.
questions short and sweet. Second, do not eat.
Yeah, we'll listen to a few questions, just see if they're interesting, see if Dr. Craig's responses to the questions are worth addressing. If they are, like I said, I might go into the Q&A. I can't promise I'll do the whole thing. I've been going for almost 2 hours anyway.
So keep it like this distance away instead of eating it, so that will prevent you from popping your peas and whatnot. Okay. Right. First question. One of these people over here, just you, and then the one next to you. We'll do it in order.
you very much for that. I was wondering, however, your insistence on the role of verification, whether that's really essential to the picture that you want to bring out. But,
Yes.
I mean, we don't no longer believe in verification, so we know that what's empirically meaningless is not necessarily meaningless, period. But it's still the case that unless you want to put God in the natural world, if absolute space and time are empirically meaningless, including spatial relativity, and if we take
I'm really sorry. I don't know where he's giving this conference at. This dude that's speaking is obviously British. But the way he's speaking is very, very annoying. I'm sorry. I had to. I'm really hoping he ends his question soon.
spatial relativity,
Look, I know it's mean, but dude, wow, that would get irritating quickly.
basically a model of the natural world, then
I really shouldn't be doing that, dude. He could have a speech impediment. I'm a fucking asshole.
absolute space and time
It's the internet. What are you gonna do?
don't play any role in the natural world. That one can still take spatial relativity at face value as showing that within the natural world there's no space for absolute place and time, while saying that it's totally meaningful to talk about absolute space and time and give them a theological significance.
Yes.
Okay, so I think that he's finished with his question there. Essentially, at least the first part of his question I was understanding. The second part I'm not so confident of. The first part he was essentially saying, well, sure, verificationism might not be preferred as or favored as an epistemological framework, but I don't think that undermines empirical data as confirmation for, say, how reality operates. So it seems that at least, prima facie, we can take special relativity as being an accurate description of what reality is, and that space-time, that there is no, there are no notions of absoluteness in space-time, that we don't, that we can take sort of at least at face value, that there really is no meaningfulness to those notions to begin with, which is something that I've kind of been saying, that this idea of verification, that we go out and we empirically look for things, and that if we can't, then they're meaningless to us. Sure, broadly speaking, as an ideology, that might not be favored, because I wouldn't prefer something like that for, say, morality or epistemology. I wouldn't be looking for empirical confirmations of things in those fields. But in the fields of the empirical sciences, I do think that I'm not going to necessarily say verificationist. That is what I said earlier, but that idea of, well, if it's not empirically demonstrated, it doesn't have much meaning in specifically the framework of the empirical sciences. I do think that, while I don't know, I would say it is the exclusive framework. I think it's a very large part of it, and I think it's perfectly okay as long as it is contained within those specifically empirical frameworks, because physics and chemistry are almost exclusively empirical. There is a bit of theorization there, and that requires mathematics, and that's not really empirical, but confirming what the mathematics is telling us does require that empirical aspect. So again, I would agree with this person's question. I think it's a very good question. Just because we can reject verificationism doesn't seem to undermine the importance of empirical data, and thereby the idea of special relativity being rooted in empirical measurements of space-time doesn't seem to undermine special relativity, and I agree with that completely.
Talk about what God does in the natural world, but that's another story.
I think it's clearly meaningful to talk about notions of absolute simultaneity and absolute length, even if these are not empirically verifiable. But I would disagree when you said that therefore they play no.
I don't know if I would agree that. I suppose there could be an ideal sense in which treatings, like, because there are events where we can treat two things that's being simultaneous. But absolute simultaneity, absolute motion, absolute space, and absolute time, I don't see. I would need to see an example of when those would be meaningful, I guess, in physics.
No role in physical.
I mean, if they're useful outside of physics, physical theories, sure, but that doesn't actually mean that they have any real physical utility. I would need to see an example, and I'm not saying that there isn't any out there, but I can't think of any. I would need to see an example of when the notion of an absolute anything in space-time, motion, causality, simultaneity, what have you, is meaningful in a physical theory.
Because if they do exist, then there is structure to space-time or to space that doesn't exist according to the Einsteinian interpretation of STR. The Lorentzian interpretation, physical interpretation of the Lorentz transformation equations, which are at the heart of the theory, is a different interpretation than both the Einsteinian interpretation in the 1905 paper, as well as Minkowski's 1908 reformulation of it in terms of a four-dimensional geometry.
That is not true. Well, first off, it was not Poincaré who developed the four-dimensional aspect to space-time. That was Hermann Minkowski, which is why they're called a Minkowski space or a Minkowski space-time. And as I said earlier, the Lorentz transformations also known. I think it's a set of 10 transformations in the Lorentz group replace the 10 Galilean transformations in the Galilean group, and the Lorentz group of transformations, the Lorentz transformations, are present in special relativity. In fact, they were used by Einstein to redefine what space-time intervals were in terms of relativistic with respect to a coordinate basis, so to speak, of a space-time. So both certainly the Lorentz transformations are very, very foundational to special relativity. And they're perfectly compatible with it. And special relativity gained further acceptance. It was made further explicative by combining space and time into a four-dimensional manifold that we call space-time. So I have to be honest, I don't know what Dr. Craig is saying here.
These differences between the physical interpretations of the theory were glossed over by the positivists, because so long as they were empirically equivalent, they could be regarded as the same theory. But with the collapse of verificationism and positivism, what we have here are different ontological structures. And so
in virtue of what are they different ontological structures, though? That was a confusing statement. Hold on here.
But with the collapse of verificationism and positivism, what we have here are different ontological structures.
I don't think the structure, like the ontological structure of space-time or of the theories that describe it, at least the accurate ones, are affected by the rejection of verificationism and positivism. I would need to hear the argument for that, quite frankly.
And so it isn't a matter of indifference. It does make an ontological difference, whether or not we're talking about Lorentzian relativity versus Einsteinian or Minkowskian relativity. Now,
that statement again, that statement seems to itself clash with the notion that they are empirically almost essentially identical, that they produce the exact same empirical or explanations and observations and things like that, which Dr. Craig has already stated. Well, and again, I would just have to ask, it's not that there isn't an answer. I can't think of one. In virtue of what, then, would they be ontologically different? I guess, in the sense that the neo-Lorentzian view still generally has an aether in it, and you could say that ontologically an aether exists in a Lorentzian framework where it does not in an Einsteinian framework. But I don't think that the framework changes ontologically there. Maybe I'm just misunderstanding what he's saying.
Whether or not this is detectable, as I say, that is right now a very controversial question on the cutting edge of physics, to which earlier speakers have already alluded.
Nobody's looking for an aether. Even back in 2012, nobody, at least no serious physicist or cosmologist, was looking for an aether, nor are any seriously calling into question the empirical aspects or the ontological aspects of special relativity.
In the violation of the Bell inequalities,
the violation of Bell's inequalities is relativistic. It has nothing to do. So just to comment on that, to sort of put it into context and explain why Dr. Craig is making that statement, he thinks that, and it's and it's not that this is not necessarily a legitimate thing to think when you immediately hear of the violation of Bell's inequality, that, well, if I can measure this particle and the other one is billions of light years away, and ideally it should take billions of years for this measured one to affect the unmeasured one, but it affects it instantaneously, that seems to violate the fundamental principle of special relativity that no information can travel faster than the speed of light. But the problem here is that they're laboring in the presumption that there's any physical transformation of information between the two entangled objects or states or systems, what have you. There isn't. No information, no physical information is physically being exchanged. All it is, it's essentially a good example, and it's a bit contrived, but it puts the idea in your head. Say that you have two balls, billiard balls, whatever. You have two balls that are coming in at completely different angles, and they hit each other, and they go off exactly in opposite directions to each other. Let's say they then travel, and now they're billions of light years apart. You happen upon one of these balls. The only thing you know about this ball is that there is another one, and that it is moving in the opposite direction of the one that you're looking at, which means that if you can determine the direction of the ball that you are near, you immediately know the direction the other ball is going in. But it's not like the ball you measured sent information instantaneously that made the other ball move in that direction. That's just the way the system works. If one is moving in one direction, the other must be moving in the opposite as a result of the interaction that was had between the two states of that system. But no physical information was transmitted there. And this is the concept of entanglement. Now, again, I was using a classical level example. It was contrived. Hopefully it made the point. But I did want to specify that Bell's inequality does not, or rather the violations of it, do not at all legitimately call into question special relativity.
By space experiments and what implications this might have for establishing absolute simultaneity. But we can leave that all aside. I think the more fundamental point is that once you get rid of verificationism, these are not impure, or these are not.
Also, if he's arguing that measurement of one aspect of the state, you immediately, like instantaneously, does something, whether it's a physical effect or not, like you would instantaneously get knowledge about the other. Well, no, not really, because again, measuring one state isn't actually physically affecting the other state. You just know what you would measure for the other state if you were to measure. And that's the thing about entanglement. It's, you know what, I'm not going to go too deep into it. I can do a video on entanglement. I think I might have already have done one. If I did, I need to look at it, because if I didn't talk about this one thing, I need to redo it. Anyway.
The same theories. These are different ontologies.
I want to say quickly, I would love to see Dr. Craig actually have a debate on specifically these concepts, time, relativity, and how it relates to God's existence, with an actual physicist. Like, if I would love to see him debate it with somebody like Leonard Susskind or Sabina Hassenfelder, somebody like Max Tegmark, even Carlo Rovelli, Alan Guth, just because I think it would be interesting. And his views on time and relativity, I've never really seen pressed by any of his debaters or any questioners at the end or anything like that. And if he is questioned on them, usually especially about his views on time, he usually just alludes to his books. Oh, well, I respond to that in my book. And I'm not going to say that's necessarily a bad response, because sometimes it's like, look, this is a very difficult thing to explain. It requires a lot. I wrote a book on it. It would just be easier if you read the book. Sure, but I do think that when it comes to Dr. Craig's view of time, I don't think that you need a book to explain it. Not saying that he should not have written one, just that I don't think you need to direct somebody to your book to explain it. Um, why he's a little bit never seems to like he's seemingly dismissive of discussions that are an attempt at really digging into his personal views on time. And that was one thing that I wanted Scott to press him on. Scott Clifton, when they had their discussion, Scott explained to me why he didn't and why he wasn't planning on it. He said, I don't know enough about the philosophy of time, and I don't understand things like relativity nearly well enough to feel confident attacking him on that front. And that's fine. Because if I ever had the opportunity to have a discussion with him, that is something I think I would probably press him on. Probably to his annoyance, but look, I want to get down to what you believe and challenge you when I think that it doesn't line up with what meaningful statements we can make about reality.
In that same vein, I want to take a little bit on your interpretation of what Einstein is up to here. I think, and I wish that Brian Pitts were here to this talk, because I think he would have been speaking about Einstein's difference between theories of explanation and theories of construction. And I think that's what he's doing in these statements. He's not giving ontological interpretation in terms of verification of what's going on in space and time in STR. He's talking about the way he was able to proceed in his theorizing in the electrodynamics of moving bodies. So by saying, look, Lorentz and Poincaré are not getting anywhere by thinking about what the smallest bits of the theory are and trying to construct something out of that. Instead, I'm going to approach the whole problem by thinking about what have we actually measured? What principles do we already have? We've got speed of light, we know that's limitation. We also know that frames are invariant, that the laws of physics are frame invariant. And so starting from those two things, we can drive all this other stuff. So when he's explaining STR, he's not saying something ontological about space and time based on the fact that he started in his paper from principles of what we actually measure. He's not saying because we have these things empirically, that's it. There's no meaning to anything else. It was just the way he approached the problem. Is that?
I think
So I really hope everybody in the chat heard her. She just summarized everything that I've been trying to express in this a little over 2 hours now stream in that 30 seconds. That Einstein was not like, look, Poincaré and Lorentz are not getting anywhere. They're trying to break up the fundamental bits of the theory and put them back together in a way that they can get this stuff out of it naturally. They're just approaching it from the wrong way. What do we know? Well, we know that the speed of light is constant, not inertial frames of reference. And we know that the laws of physics are invariant in all inertial frames of reference. And those were the two fundamental postulates, are the two fundamental postulates of special relativity that Einstein worked from. And from that, he derived the relativity of simultaneity, and he derived the notions of, utilizing the Lorentz transformations, which were already incorporated into electromagnetism. He utilized those and redefined what space-time intervals are and said, okay, from this we get length contraction, we get time dilation, the speed of light being constant, the invariance of the speed of light work under these transformations. It means that these transformations are very good. They really, really help us mathematically quantify what is going on in this theory. And he just kind of took what electromagnetism was telling us and said, look, I can make it work with this particular framework. If we use special relativity as a framework for understanding electromagnetism, it all seems to just fall together and fall into place very, very well. And that's that is the case. He wasn't necessarily making ontological statements about anything. He was simply saying, look, this is what we know, and this is the best way forward. Let's use this framework for interpreting this. And when we do, we get the most accurate results, and it all just flows together beautifully. And I'm curious to hear Dr. Craig's response here, because she just worded it beautifully, absolutely beautifully.
you're quite right in distinguishing between theories of explanation and theories of principle, and that this is a theory of principle, as you say. The special theory, as Einstein developed it, is explanatorily vacuous.
Not really. Because again, the behavior that it tells us for what happens when things are in motion in space-time helps us understand more about how reality works. It explains why you have some of the effects, not just in electromagnetism, but in cosmology, relativistic jets, relativistic quantum field theory is called that for a reason. And it's not, I don't want to say incorrect, I don't want to say it's not correct, but it just doesn't work well without special relativity. In fact, we didn't really have a complete description of electrodynamics, chromodynamics, any of that until we incorporated special relativity into the model and developed relativistic quantum field theory with the work of people like Wilczek, Weinberg, Feynman, Dirac. These men later on really helped refine that field. And a lot of the effects that we observed in reality could not be explained without special relativity as a framework. Special relativity is a theory, but it's a very broad theory that is more of a framework that we use for looking at reality. The ways in which we need to interpret how things in space-time will behave with respect to that space-time. And what we find is that space and time are not absolute. They are combined into one four-dimensional manifold, and that they are dynamic. They have an effect on things inside of them, and things inside of them have an effect on them.
Three-dimensional objects that undergo these deformations as they are in uniform motion relative to each other are real physical deformations. These rods actually contract up, but the clocks actually slow down. This isn't mere appearance. And there's no explanation for this at all.
Well, there is an explanation for that. Well, why space-time curves under the stress of mass energy is not understood. That it curves under stress from mass energy is explained quite well through Einstein's field equations. In fact, William Lane Craig, at the beginning of this, I think that was when we were having the audio issues, even said that the Alexander Friedmann's solutions are exact solutions and describe a dynamic space-time, and they do. Why lengths contract and why times dilate under certain transformations, like the Lorentz transformations, is a result of the structure, I guess you could say, of space-time changing. The way that coordinates exist, the way that objects exist within space-time changes when you start going really, 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 really fast. That's it. That does explain these things, and we can see that reflected in the space-time diagrams. I just want to say a lot of these, because I have to be, you know what? No, I'll save it till the end. I'll save it till the end.
Say in the original paper, they are simply deductions from the two postulates. But what's critical to see, and here is where I think that you're overlooking something, is that those two postulates are not themselves empirically established.
So again, he's referring to the two postulates of special relativity. Number one, the speed of light remains constant in all inertial frames of reference. And two, that the laws of physics remain invariant in all inertial frames of reference. And those have been empirically confirmed. And it's not just that they've been empirically confirmed, it's that literally we do not get accurate descriptions of reality without them. We know reality is preserving them. That's part of the reason why Einstein developed special relativity, because he needed a framework for explaining the phenomena that we are beginning to observe in a way that does preserve the constancy of the speed of light, which is empirically demonstrated, as well as the invariance of the laws of physics under the Lorentz transformation, something called Lorentz invariance. So it's not just that, in fact, they have been empirically confirmed, and they have, again, you don't have to take my word for it, go ask a PhD physicist. It's that we have to assume them to be true in order to make accurate measurements about reality in the first place, which seems to itself substantiate the fact that they are accurate statements about how reality behaves.
The postulate.
And just to add on to what I said, just because some sort of proposition or postulate may be a priori does not mean that it's false. So I could grant that they may be a priori postulates, but that does not mean that they are false. to be postulated?
Of the sameness of all physical laws in every reference frame is based upon the assumption that absolute space does not exist. Otherwise, the two postulates of the theories are in contradiction to each other. The two postulates cannot both be true unless you presuppose that absolute space does not exist. So,
Well, if we have to presuppose that those don't exist, and we can't get accurate statements about reality without using the two SR postulates, that seems to infer that the notions of absolute space and time don't exist, which is why we have to use these postulates to explain reality to get accurate results. I'm just, I have to be honest here. I'm baffled that someone like Dr. Craig can't connect these dots. And this is why I'm wondering how much about the actual history of the development of special relativity and electrodynamics has he looked into? Or did he just cherry pick some work to find some quotes from theistic scientists or from scientists that are theistic in order to support, by the way, to support his personal beliefs?
so that's why I said the theory doesn't really disprove absolute space and time. It actually presupposes it. And those twin postulates, you cannot be established empirically. They are, as you say, just postulates.
Yeah, but if you just attacked the idea of utilizing empiricism or verificationism, which is through strictly empirical means, otherwise through just logical truths. So how can you then say, oh well, it's not rooted in, it assumes this empiricism, this, that, and this, whatever. It's entirely resting on, empirical confirmations, and then say, oh, but you can't empirically confirm these. But it seems that you're already granting that we shouldn't rely strictly on empirical confirmation when you reject that notion, when you attack special relativity. To then turn around and say, oh well, you haven't empirically demonstrated these, seems like he's talking out of both ends of his mouth here. I don't even know how many people are listening, but please tell me I'm not the only one seeing this. Anybody who watches this back in the comments, please tell me I'm not the only one seeing this. And again, sure, they might not be empirical. Let's grant that they're a priori postulates. Why should I believe they're false? Or why should I not postulate them when trying to make empirical statements about reality? Especially when it seems that I need to, because if I don't, I won't get my answers will not match my observations. But when I do assume the postulates, the math does match the observations. The theory does match the observations. Why is that? Why is it that reality seems to be telling us, hey, look, if you don't make these assumptions, you're not going to get accurate answers? Why?
Just principles that one accepts based upon the assumption that absolute space doesn't exist. And that assumption is rooted in this epistemology of verificationism that says if you can't detect it, it's not real. And Lorentz, in his correspondence with Einstein, came back to this over and over again. He would say, just because you can't detect something empirically doesn't mean it's not real.
True, but in physics, it means that it's not useful to us. Why should we postulate an ether that we cannot detect, especially when we don't even need it to explain anything? When it doesn't add any extra explicative power.
And so the great predecessors of STR, like Poincaré and Lorentz.
And just another thing quickly here. If special relativity is this like unverified presuppositional thing that is like seemingly only conventional and we don't really need it, why is it utilized by most physicists? Why are no physicists, and why haven't they for over 100 years been scrambling for something different, something better? Why? Why not? Dr. Craig likes to cite a consensus on a lot of things, such as, the historicity of certain aspects of New Testament, the historicity of Jesus. Why is the consensus of physicists as well as the philosophers of physics not enough for him here? Is it because the conclusions of special relativity clash with conclusions of, or rather premises and arguments he likes to give to support his personal beliefs? Is it because special relativity clashes with his personal beliefs?
We're never convinced that Einstein's interpretation was right because they didn't accept the postulates.
And I just have to reiterate this because this is a very important point. It wasn't that the laws of physics remaining the same regardless of how we transform in space-time was something we just assumed. We don't get accurate mathematical descriptions of the physical systems we're attempting to describe if we don't assume it. That, and I know I've said that a couple times, but it's important to remember, if you stop assuming these two fundamental postulates, you don't get accurate descriptions. They are, both of these things are also assumed in a neo-Lorentzian framework. Because as Dr. Craig himself said, the Lorentz transformations, which preserve the invariance of the laws of physics, when you use those transformations, are present in a neo-Lorentzian framework, as is the speed of light being a constant. So even in a neo-Lorentzian framework, those postulates are assumed. In fact, they're more assumptuous, or I guess you could say presumptuous, in a neo-Lorentzian framework than in a special relativistic framework, where they are assumed, but they also seem to just like fall out of it naturally.
So thanks very much. This is just a question of a request for clarification on terminology, I guess, really. So it is, and I'm sure you're familiar, the words absolute was
Yes.
reference to space and time can be used to mean a number of different things. And one of the things that absolute often gets confused with is the idea that there's a preferred frame of reference.
That's why.
That there's a preferred frame of reference. So, I mean, as you said a minute ago, the real difference between these interpretations is an issue of what we take to have to be a part of the structural foundations of the world, the structural foundation of space-time. It's a structural issue. And the idea that there's a preferred frame of reference is the idea that space-time has more structure or less symmetry than it may under another interpretation. So how much does any of this really hinge upon whether or not space or time or space-time exist as entities? And how much is it an issue of what kind of structure those things have? So I mean, but really, I guess I could just say the question is, can I be a relationalist, not believe in substantial space-time, and still take your side on this just because?
Absolutely.
Okay.
Yes, I think so. And in my book on this, I list and explain 6 different meanings of the word absolute that are in the literature. Absolute relational, absolute versus frame dependent. The word is used about 6 different ways. I mentioned 2 of them in the paper today. And any of these theories can be given a space-time formulation in terms of this 4-dimensional geometry. But if you hold to a tense view of time, according to which temporal becoming is real, then I think you should reject the Minkowskian 4-dimensionalist space-time realist view, according to which the future is just as real as the present is as real as the past. And if you do that, then if Minkowski is out, what you're left with is either Lorentz or the original Einsteinian interpretation in the 1905 paper. And as I said, that 1905 paper is explanatorily vacuous. It posits these mysterious deformations of 3-dimensional objects without any sort of explanation at all for why it occurs.
There is an explanation. Lengths contract because the distance between the 2 points that you're using to define the length will do this under these kinds of transformations. In the time dimension, they will do this under these types of transformations. Lengths contract, times dilate. Actually, times dilate to 0. They get slower. The speed of light in the direction of your travel, length would contract to 0 and time would dilate to 0. You would not measure any length in the direction of your motion at the speed of light, and your clock would read no elapsed time at the speed of light. So the reason that these effects take place, and anybody who's actually taken a course, like an actual physics course on special relativity or on relativity, or who has at least, like me, read some like textbooks on it and watched some lectures on it, like Leonard Susskind's The Theoretical Minimum lectures knows, that it's the change. You well, I use this word, it makes it sound like you're using a vector space, but it's really the only phrase I can think of, is that there's a change of basis. There's a change in the coordinate basis that you're using under these kinds of transformations that physically affects the objects that you're transforming. So what we would measure that as in terms of a physical effect would be a contraction of lengths and a dilation of times. So in fact, it does explain this, and physicists would say that it doesn't. They would just point you to the change of bases that occur. Again, I'm using that term and not referring to vector spaces, which I don't really think it necessarily needs to begin with. But because the axes are changing, there's going to be a change of the basis coordinates that you're using to form all that you're combining to form any other coordinates. So, and this is how it also is in general relativity. As you parallel transport a vector across, curved in space-time, you're going to get a tangent plane that changes. You're going to get a change of basis. So, this rejection of special relativity seemingly would have to come alongside a rejection of general relativity. And I would wonder if Dr. Craig is willing to do that.
And the Minkowskian also sees this as a deficit of the relativity interpretation, and instead wants to postulate a four-dimensional geometry.
Well, again, the four-dimensional geometry essentially falls out of special relativity. If the way that special relativity is written without it, the way that the equations work without it, essentially gives you a four-dimensional space-time in which space and time are connected, which is why, or rather how, Minkowski developed that from Einstein's formulation of special relativity. He looked at how he formulated it, the way he defined his equations, and said, well, look, you can just take space and time as being connected into a four-dimensional manifold as space-time, and everything stays the same. In fact, it actually helped bolstered special relativity. It put it into a further framework that helped it to make sense.
If you hold to the objectivity of temporal becoming and tense time, then you're going to throw out that space-time realism, and I think have a tense theory that is more plausibly Lorentzian than Einsteinian.
Sure, and if I can just to clarify, then, but it is an issue of what kind of structural properties the material world has. I mean, you could even say that time, space-time, whatever, does not actually exist, but your perspective would then translate to a claim about what kind of structural properties the material world has.
My only hesitation is when you say material world, because you see, I'm as a theist, like Newton, I want to root this absolute simultaneity and absolute now, the present, in God's time, which isn't material. I would see.
So I guess that what that means is that Dr. Craig doesn't actually believe that space and time are like real physical properties. Maybe I'm just misunderstanding. I mean, if that was the case, I can't say I would be entirely too surprised. I mean, they are that general relativity. They're real. They're real. They're physical. They might not be fundamental. They might be, but they are real and physical. Space and time. Space time is a real physical manifold.
Material realm as being derivative from God's metaphysical time. In fact, when you think about it, it seems to me that the universe is a clock. The universe is God's clock. It measures the duration of God's absolute time from the moment of creation forward in cosmic time. So
that doesn't make a lot of sense, though. I mean, time isn't a thing that flows. So you would have to be looking at things in the universe and that change in a very periodic manner that is very repetitive and consistent in order to really consider it a clock.
I hesitate with respect to saying of the material world, but yes to what you said about postulating the structure of a sort of hypersurface of simultaneity on which present events exist and with respect to which temporal becoming is an objective feature of reality.
So if I understood correctly, all this problem started with the probably absence of frame, of a special time frame in Einstein's theory. But actually do have an absolute frame, which is the speed of light. So given that the Bible identifies a lot God with light, doesn't it appears to me that God does not live in time, but furnish time with reality and act also as a reference for time happiness?
Well, now, the speed of light being the same in all reference frames doesn't serve to define a unique frame in the special theory.
That is true. Primarily because your two axes in your space-time diagrams converge onto the 45-degree line that comes out from the origin, which represents the speed of light. You don't really have a reference frame there of sorts. So yeah, Dr. Craig is correct there. The speed of light doesn't form some unique frame of reference in relativity.
But with respect to God, I haven't given any arguments here for thinking that God is temporal, but I do that in my other work. And would argue that given a tensed view of time, that God's omniscience, knowing the truth of all tensed truths, and his causal connection to a world of temporal becoming necessitates that God is in time. So I give independent arguments for thinking that if God exists, he's temporal in view of his omniscience and causal connection to the world. And critical here will be your theory of time. I'm presupposing, well, and arguing for a tensed theory of time.
Yeah, I didn't hear much of an argument for a tensed view in any of this, which is a shame because I did want to get into tensed and tenseless views of time, but if it's not like a major aspect of the video, then I don't really want to comment on it. I can save it for another video.
So you stated, if I understood correctly, that there is this absolute reference frame, and it's when I'm moving at a velocity with respect to this absolute reference frame that the meter stick changes size and the clock slows down.
Yes.
Wouldn't that give an empirical way to find the absolute reference frame, because we just look for the one with the longest meter stick and the shortest second?
No, because for observers in motion relative to the absolute frame, there isn't any way to empirically detect that you're not the one at rest and that the other frame is the one that's moving. So unless these recent experiments with respect to Bell's theorem and the violation of the Bell inequalities suggest that these two photons have relations of absolute simultaneity between them, either when the quantum collapse occurs or they're correlated in some way. That would be the best way of establishing relations of absolute simultaneity. And so people like J.S. Bell, for example, advocated going back to Lorentz in order to best explain the violation of the Bell inequalities. Otherwise, what you get are causal influences going backwards in time relative to some frame.
Just again to reiterate, there is no direct physical causal link in entanglement. That's not what entanglement is. Also, this whole notion of an absolute reference frame, how do we even define one? Absolute with respect to what? Because if you say, well, this frame is the absolute one and then this is the moving one, I can just make this one stationary and then move this one past the initial frame at the same speed. You were telling me this one was moving. For instance, say you're in a car going down the road at 100 kilometers an hour. You pass by a post. There is no mathematical difference whatsoever from the car moving past the post at 100 kilometers an hour or the post moving past the car at 100 kilometers an hour. Which one then would be the absolute reference frame? Which one is truly the frame at rest? See, this is part of it. The whole absoluteness makes no sense. It has no meaning in physics. It just doesn't. absolute with respect to what we could technically make any frame of reference the absolute frame of reference if we really wanted to, which in turn means that no frame of reference is truly absolute.
But if you have relations of absolute simultaneity, then you won't have that. So that would be, I think, the best bet empirically of establishing this preferred frame.
Yes, well, thank you for your talk. There's something I came across recently in a book by Lee Smolin called The Trouble with Physics. I don't know if you've come across this at all. He points out something which many physics graduates, I mentioned for many years, is that there is at least one absolute distance length in physics, which is the Planck length, which doesn't scale up or scale down. So it's an interesting thing, it's a little fact that often gets missed when people talk about being able to transform any length into any other length, depending on the reference frame, but the Planck length doesn't. So there's an interesting, I know there's some variations of special relativity, like double special, there's something called doubly special relativity, and some extensions of relativity, but they do involve absolute distance lengths.
I'm not familiar with that, nor have I read Smolin's.
So the Planck time, number one, I don't know if I would say it's absolute anything. It's simply the smallest unit of distance at which the laws of physics still have any level of meaning. It does not necessarily mean that there is nothing smaller. It just means that currently our physics is meaningless at scales smaller. Also, the Planck length is defined as the distance that a photon will travel in 1 Planck time, I believe. So unless I have that backwards, or 1 Planck time is the amount of time it takes a photon to travel 1 Planck length, which, I mean, I guess they would be backwards, but I think it was originally derived from Planck time, but don't quote me on that. But it doesn't really pose any problems for special relativity.
Book, so I can't comment. Thank you.
You mentioned, or you said that in the absolute time, the universe is or is like God's clock. How does that work?
Well,
how could it be a single clock?
Yes.
In the universe that we know.
As the universe expands, there is a kind of natural geometry in which the universe is homogeneous and isotropic. And you can then establish a cosmic time parameter that will measure the proper time of the duration of the universe back to its beginning. And it's important to understand this is not a coordinate time. Time is a parameter here that is independent of spatial coordinates. So it's not part of the space-time coordinates of events. This is a parameter which is independent of spatial coordinates and gives you how long the universe has existed. So when people say the universe is 13.7 billion years old, they're not talking about Earth time, they're talking about cosmic time. And this is the same for every observer in the universe, regardless of his state of motion. The universe in cosmic time is about 13.7 billion years.
The thing is, he's presupposing an A theory when he says that. Under a B theory, to future humans at some point in the future, who would be just as real as we are, even though we're not co-extended with them through time to be experiencing them or what it's like in the future is still real. Obviously, if they're humans a billion years in the future, they observe the universe being 14.8 billion years old. So no, they would not observe the same time as us. You have to presume that time is not tenseless in order to make that statement, and well, given special relativity, time is tenseless. So I feel like Dr. Craig would almost be arguing in a circle again if he just assumed the time is tensed to argue against anything that the special theory of relativity says. So, and just again to reiterate, cosmic time is arbitrary. It is the ideal scenario in which we consider a clock that exists independently of the expansion of space-time as well as any mass energy in it. It is a clock that ideally, meaning that such conditions don't actually exist, we just convent them for utilities purposes. this is a clock, an ideal clock that has no time dilation effects on it, and that was set at 0 at the moment at which the earliest moment that our physics can take us to, which is itself, it's abstract, but it's not, because we can go before it. We just don't know how, because we don't have the physics. But if we arbitrarily set the clock at 0 at that point and let it evolve with no time dilation effects, we would measure a universe that is of an age of about 13.8 billion years. But that's only relative to our location in space-time. Anybody else located at a different point, especially if their time coordinates are different, could measure a universe which is younger or older. So even this is not exactly correct.
Old. And my suggestion is that that would be the natural measure of how long it's been since God created the world. So what could be clearer than that? That for God, it was 13.7 billion years ago that he created the world, and the universe is, in effect, a clock measuring how long it's been.
Where do you get that unit of years?
Where do I get what?
We use the unit of the year.
Oh, I see.
So where do we get these units?
Well, those would be arbitrary, obviously. I mean, that's a convention, but I mean, we get it from the Earth's orbital motion around the sun. But the interesting thing is that the Earth is very nearly in rest with respect to the microwave background radiation, which seems to coincide with this cosmic time. So we actually have a pretty good idea of what time it is in cosmic time. The Earth is slowly moving in the direction of the constellation Leo at about, I think, 360 kilometers per second or something like that. So that we have actually a pretty good measure of cosmic time using our clocks here on this planet.
Well, of course we use our clocks. Even cosmic time is still measured. That clock still is measured as ticking at 1 second per second. And a second is a thing that humans invented. We didn't find a second lying around in reality.
It's quite remarkable.
This actually speaks to this very last question. So on your view of Untitled, there is a preferred frame which God is sensitive to, but we're unable to identify. So is that not itself somewhat surprising? Why should this be hidden from us in this way?
Now, you know, I don't see any reason to think that if there is this sort of preferred frame, that it would need to disclose itself to us. In fact, these deformations are necessary in order to maintain the equilibrium of systems in motion so that they aren't destroyed. So that the hiddenness of the preferred frame, in a sense, could be an indication of the providential care of God. It's due to these sorts of deformations that physical objects are able to maintain their internal equilibrium.
I would just say that I don't think there's any notion of an absolute time. Seems to be the much simpler response.
But in cosmic time, there I do think that this preferred time is revealed because of the expansion of the universe. We are able to detect what time it really is.
Oh, we don't actually deduce it from the expansion of space-time alone. We have to make numerous corrections to that derivation that account for mass and energy and radiation and dark matter and dark energy. So all of these things come together and hone us into the age of the universe. And the age of the universe can only be, it's 13.8 billion years. And I think that the only variance that can be allowed is, I want to say, like 200 million years, which is not really enough to affect it when we're already talking about practically tens of billions of years. But yeah, it's not just from the expansion of space-time alone. We also have to consider the content of space-time as well, and the various percentages of the different aspects of the content of space-time to accurately determine its age.
And it's remarkable how the old classical ether has come back into modern physics
No, no, it hasn't.
Under new guises. For example, I've already mentioned the microwave background radiation,
The microwave background radiation isn't an ether.
which is the microwave equivalent of the luminous ether of the
No, it's not the microwave equivalent of the luminous ether, because electromagnetic radiation doesn't propagate through it.
19th.
It is electromagnetic radiation. What? So the question here would be, if the cosmic microwave background is the ether, what is the electromagnetic radiation that makes the CMB up propagating through? It's electromagnetic radiation. I'm sorry, that was an absurd statement to say that the CMB is the ether that the CMB would need to propagate through to begin with if there was an ether. What?
Century, and we can actually detect the ether wind of our motion through the microwave background radiation. The quantum mechanical
No, actually, there aren't any variations in the CMB when we consider Earth's motion.
vacuum also is like a modern ether that coincides with this, and the preferred frame of expanding space. So there are quite a number of these sort of ether frame equivalent notions in modern physics that does give us, I think, that do give us rather a good idea of what time it really is. So I don't think
But none of these things is actually even remotely equivalent to what the ether was posited to be. Nothing.
nature is conspiring to
And again, it's worth mentioning that we cannot detect the ether. It's unfalsifiable. We don't know what it's made out of because we can't measure it. We've tried. It's claimed that you can't measure it. It's an entirely unfalsifiable assumption that was in no way, shape, or form needed to explain the reality we observe.
conceal this from us.
What happens to God in time when particle encounters a black hole and approaches the singularity?
Right. The deviations from cosmic time that occur are due to either local gravitational effects or the type of motion that comes into view in the special theory of relativity. So cosmic time would
That is correct, because cosmic time is arbitrarily decided to be a time independent of any gravitational effects or any effects of unique motion.
define a kind of worldwide parameter that would measure the proper.
So just again, cosmic time is an entirely arbitrary thing. It's not, there isn't a physical thing that is cosmic time. There isn't an actual clock reading what cosmic time says. We've arbitrarily made it that way.
Time of the universe. But locally, as in black holes, this will become distorted because of gravitational effects. Wheeler, Thorne, and Misner in their book on gravitation describe cosmic time as many-fingered. When you get into these black hole areas, it's like fingers, so to speak, in cosmic time, so that at the terminus of a black hole, it's the end of the universe there. It's the end of time. So I'm talking about these broad hypersurfaces globally that represent cosmic time, but you're quite right in saying in black holes and other local phenomena, you wouldn't have cosmic time registering this sort of global parameter. The deviations from cosmic time will be due to just local phenomena. So relativity is reduced to a local phenomenon, not a global one.
Next to you. Did you have a question? No? Okay, take it away. You, okay, then we're going to have time for one more after that.
I'd like to press you on this idea that the universe would be God's clock.
Yes.
Now, of course, if you go back towards the time when the microwave background radiation was created, then you actually have, you can measure the passage of years. And our civilization today measures the passage of time by the oscillations of cesium atoms. What do you do when the universe is the size of a cesium atom? I mean, ultimately, all your clocks are going down with you into the singularity.
Right.
So how do we resolve this?
Well, ultimately, this will break down, as you say, when you get back before the Planck time. Then you're not going to have any sort of physical mechanism that is going to operate. But I don't think that means time itself ceases to exist. It just means that you won't have a clock at that point. I think you're quite right about that.
Well, yeah, Dr. Craig is correct there. At that time, there would still be physical phenomena going on, but it's not very well understood at the given instant, and we wouldn't know what to use thereby to really measure any passage of time. Um, So, I mean, his question, it was a good question, but in terms of answering it and getting, I mean, this is really getting in the weeds now with like Big Bang cosmology and particle physics and how are we measuring the passage of time? We've got all this gravity compressed in this very small space. You know, what are the dilation effects? That's really getting in the weeds, and I don't think I'm really up to the task of fully explaining it, to be quite honest.
Did you have a quick follow-up?
It's not a follow-up.
Oh, is it quick though?
I can ask you a question.
Okay, good.
So I have a good feel now for your reasons for referring to neo-Lorentzian approach to space-time and Einstein as it was in 1905. If you were to compare, say, the approach to space-time that we get from Minkowski in 1908, 1909, I don't yet have a really good understanding as to why for the neo-Lorentzian approach, other than the fact that it's more compatible with the view that you presented on calculation of time. Do you have any other reasons for referring to
Well, my main reason is because I'm just so deeply committed to a so-called A theory of time.
Yeah, so here he's essentially admitting it. I take a neo-Lorentzian view mainly so I can rescue an atheoretical view of time, because things like time dilation and the relativity of simultaneity, and thereby the relativity of what we're defining, the sort of arbitrariness of defining past, present, and future seems to indicate that time is a tenseless thing, because then what that would mean is that defining the present is arbitrary. The present is relative, and on Dr. Craig's view of presentism, only things in the present would exist, which would mean that existence is relative. And since no two clocks of any objects in time are going to read the exact same time, no two time coordinates, I should say, in a very, 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 very small amount of instances, are there going to be any two time coordinates that line up perfectly. And what this would mean is that with respect to any other object, some object doesn't actually exist, because albeit infinitesimally small by an infinitesimally small amount, it's still either in the future or in the past with respect to the object from which you're measuring, because those clocks are not perfectly synchronized. So if existence is relative, that seems a little interesting. So he's pretty much saying that he doesn't really have any real empirical data here to back up his preference for a neo-Lorentzian framework. It just helps him reconcile an atheoretical view of time with the observations that we've made concerning time.
A tense theory of time. In fact, I think that what really carries the water in this argument isn't so much God as the tense theory of time. Because if temporal becoming is an objective feature of the universe that is mind independent.
It's not. And I want everybody to consider this for a second, because this is what really does it for the A theory of time, which posits that temporal becoming, things coming into time, is an objective, real feature of reality. What this means is that these are things that are not extended through the space-time manifold. They then somehow get into the space-time manifold, persist within it for some time, and then sometime get back out of the manifold. What? What does it mean for something to enter into time? How did it get into time? Where was it prior to that to come into time? And by what mechanisms does that occur? The very notion of entering into time, of somehow getting inside of the space-time manifold when you were previously outside of it, which doesn't even make sense. It's like saying north of the North Pole in itself. How does this happen? When have we ever observed this? There are serious issues with not just the A theory, but more specifically a presentist view of time. Major, major problems. And they primarily come from special relativity, but as well general relativity. And Dr. Craig has pretty much admitted this is the motivation for his rejection of SR, not really anything else.
Then it is simply not true that all events in space-time are equally real or on an ontological par. And there are all sorts of other deleterious consequences to space-time realism. I think it implies, for example, perdurantism with respect to personal identity over time. I'm literally not the same person that walked into this room this morning. I'm a later temporal stage of a four-dimensional worm, but not the same as the earlier stage. And this has all kinds.
Well, that depends on what you mean by the same. And, you know, identity as it relates to time and persistence through time and identity through time is, again, a little bit deeper than what I'd really like to go, especially since we're getting close to the end of this and been going for almost 3 hours. So I would like to wrap things up.
Of crazy consequences for personal identity, moral responsibility, and so forth. So in my book, again, I lay out my best case against the tenseless theory of time, and hence this Minkowskian space-time realism which presupposes it, as well as thinking that there's no good reason to adopt such a breathtaking metaphysic of the world as to think that our experience of temporal becoming is an illusion, and that all events, whether past, present, future, are equally real. It seems to me that's a gratuitous reification of a diagram in which space and time are plotted together on a piece of paper, but there's no reason to invest that diagram with actual reality.
Well, it's more that the effects that arise from these diagrammatical depictions of space-time are directly measurable in space-time. We've measured muons being created in Earth's atmosphere from high-energy cosmic rays, and we've measured the time dilation effects, and as well as the length contraction effects in the direction of their measure by being capable of detecting them before they decay, despite the fact that they should decay before we measure them. But because their time dilates, we're able to detect them. We have to consistently readjust the clocks on our GPS satellites. If we did not do this, they would be off in a 24-hour period by 7 miles. These are actual, physical, real, tangible effects in reality that we measure and have to actively account for if we want to accurately get to places on the surface of our Earth. If we didn't readjust those clocks on our GPS satellites, which are far above the Earth and thereby further away from the source of gravitation, and so the gravitational time dilation drops, the clocks tick slightly faster than clocks on Earth. So if we didn't make those adjustments, planes and ships and your phone would be off by miles upon miles, 7 miles every day. We actually have to correct for these effects in reality. We actually measure them in reality.
We're out of time now. So we got coffee. Like I said,
Alrighty, and that wraps that up. So I can stop sharing. So in terms of my final thoughts, the argument that Dr. Craig seemed to give was that, well, you know, verificationism and positivism have been rejected. So the fact that special relativity is empirically grounded on certain things doesn't necessarily confirm that that is the way reality is, which I think is a bad argument. And therefore, we can reject special relativity because of its faulty foundation and adopt a sort of a neo-Lorentzian view, which allows us to rescue the notion of absolute time, absolute simultaneity, and thereby we can say, well, that's just God's time. I'm just being honest. I would wonder the extent to which Dr. Craig has examined the history of special relativity and the thoughts of the men who developed it, because I don't think it was very accurately represented here. I think that some of the statements he made really just didn't even make sense. His statement about the cosmic microwave background potentially being a candidate for the aether, that which electromagnetic radiation, which is postulated as a medium through which electromagnetic radiation propagates, and the cosmic microwave background is electromagnetic radiation. So if it's the aether, then what is it propagating through? Itself? That doesn't make any sense. What's the argument for that? What's the data for that? There's just a lot of misconceptions in this video about relativity, about time, and a shoehorning of ideas into special relativity as justification for rejecting it to rescue one's belief in the existence of God. And this is why I do this. This is why I make these kinds of videos, because I think a lot of these misconceptions and misconstruals of the science, and even of certain philosophical aspects of the science, need to be called out. And while I am not a professional, I think that I understand these things and can understand these things well enough to be able to share my thoughts in, I think, an adequate manner, and hopefully in a manner that everybody else listening finds entertaining, because that is obviously a large part of why I do this. I find it entertaining, and I hope at least that a lot of other people do. But with that, I'm going to end the broadcast, and I will put the link to that video that we've been watching in the description from below if anybody would be interested in watching it all the way through without the interruptions. And it's just a good thing to link that kind of material. And with that, remember, folks, through reason, we progress.